Tiger Beetle Sessions, Tuesday, 14th December, Session 3. Hey, Yoran, what's up?
Hey Isaac, pretty good this side. Looking forward to vacation next week, and the Beatles are back. So pretty chuffed with this new Tiger Tracks tee uh, for the
Nice.
Tiger Beetle sessions. And hey Larice,
Morning, everybody.
uh,
All right.
yeah, enjoyed
We'll jump
yesterday.
straight into
Yeah, we
it.
can jump into it. I'll just recap. Should we do that quick?
Sure, yeah.
Yeah. So yesterday was pretty exciting. We were thinking, how do we keep track of all the metadata for all these LSM tables? So we've got like 2 million tables. Each table can be like up to 64 megs. And we've got about 64 bytes of metadata per table, 2 million tables. And given a key, for example, like for a key value, we need to look up this key very fast. So the problem that we're solving is, given a key, find all the tables at different levels in the tree that could possibly contain the key. So each table in the metadata, which is 64 bytes, we've got a min key for the table and a max key. So this problem is all about, given 2 million tables with key min, key max, find all the ranges that intersect and find it really quickly. And to compound the problem is we've also got to do static allocation, and we don't know, we've got 30 LSM trees, something like that, like on that order, and we don't know how big the trees will be relative to each other. So we've got a big pool where we can statically allocate all these metadata 64 byte objects that could be used across a total of 2 million tables, but we don't know where the split is. So which of the trees are going to have most of the tables? That's all dynamic, and we don't know what that is. So what we settled on yesterday was the strategy where we've got a big pool, all the possible metadata objects. We're going to let the different trees claim them as they need it. And then we basically went from, how do we represent the table metadata? Isaac, what do you how,
Yeah.
you want to take us from there?
Yeah, so we've gone through now several iterations of this design. When we started out yesterday, we were thinking, um, well, Jordan had this important realization that we could split up, we use a pool allocator and like just allocate blocks of memory. And then the question is then how do we then search these across these blocks of memory? And so our first like just naive thought was just use a linked list between the blocks and then do a linear scan over the whole list to find stuff. That's obviously quite slow. So the natural like step after that for like just building indexes to search a linked list of blocks of items would be to use the data structure that is literally that, which is a B tree. It's basically just that data structure, but with then several layers of tree on top of this to make searching O log n instead of O n. But then I guess we just don't, it doesn't really fit perfectly with our like design because then you use a lot more data for overhead and it's also not terribly fast. And it's a little bit complex to implement. And so our current iteration is kind of goes is closer back to the linked list, but instead of using a B tree to index it and speed up lookups, we're using our Eytzinger layout, which you can read more about in the paper Array Layouts for Comparison-Based Sorting. This is a basically a binary search tree, but laid out in order so that the CPU cache plays very nicely with the performance characteristics. And you can then look at each node that you want to look at is kind of laid out in order. So you have first the root node, then the two children nodes, then the four children of those nodes, and then the eight children of those, and so on in a contiguous array in order. And so that means that during the binary search, you always scan in order and through contiguous memory, which makes things very fast. And so we've already got an implementation of that actually in Zig in Tiger Beetle. And so now we're planning on using that to speed up lookups into our index nodes or into our basically our unrolled linked list. We've also done a little bit of changes to the linked list design to speed up indexing, hopefully, to make random access faster. Um, and we can maybe show those in code better and talk about them.
Yeah.
I'll share my screen and we can get going with that, I guess.
So the unrolled linked list is where nodes in the list contain more than one element. So you get better layout in the memory, less cache misses, much more performance. But at the same time, so it's basically you have batches of nodes, elements in a node. So unrolled linked list is you can tune the structure. It's somewhere between being a linked list with all the really poor performance or being a fixed array. You can just tune the spectrum, where you want the unrolled linked list to be. But it's pretty nice because it lets us do the pool allocation. So we can share these nodes across all the trees. And then, like
Yeah.
Isaac said, we're going to index into this big unrolled linked list at the bottom with a little Eytzinger accelerator. Yeah.
Yeah. And so where we're at right now in the code is that we've just switched designs from using a linked list of these nodes. So we've got here like 2 tiers of nodes. The first tier is index nodes, which store this information. It stores like the total number of elements in all the child data nodes. And it stores a number of data nodes that are currently present, and then pointers and lengths of all the child data nodes. And this allows us to more quickly scan through the list to access a random index, because then you don't need to do the cache misses to go through each of these data nodes and see how much data they've got stored. You can then potentially skip over a whole. This number ends up being like 340 with the actual key sizes we use in practice, or in that order of magnitude. And so you can skip over 340 nodes if this index node doesn't have the thing you're looking for. Otherwise, you just scan this array till you find the one you're looking for, and that's about it. But we've now changed our strategy here. Currently, we have a linked list of index nodes implemented in the code using this nice fancy XOR trick to only have one link per node. But we've actually decided to change the strategy here to make random indexing faster, and also just gives like a little bit better and make things simpler too, because this
Yeah.
XOR trick is a little bit tricky. You gotta like do XOR and pointer to int to make it work, which is implemented correctly right now. We're pretty sure, but it's still like a little bit on the borderline of like where we want to go complexity wise. I feel like, and so our new plan is to just allocate a slice of index node pointers, and we can statically know what the maximum number of these will be based on this. We've got here in our config like the table maximum number of tables would be support, which is currently 4 million, power of 2, just over 4 million. And then we can just divide that by the number of table infos per index node to find the number of index nodes we will need. Should be a break statement, and we should be using div seal here.
Yep.
But yeah, as I said, we changed design right as we were leaving off yesterday.
Yeah. So
And now we need to actually implement the code, it seems.
it's pretty interesting. Like what we've done is like in a linked list, the metadata for each node, the metadata and the data is stored together in the node of the linked list. Unrolled linked lists, the nodes are bigger, containing many elements. So you can make them a multiple of cache lines, get really nice performance, amortize your metadata overhead because you just got a previous pointer, next pointer, account. That's your metadata. But what we've done now is we've kind of taken it to the next level. Like now, the unrolled linked list nodes is pure data. There's just data in there. There's no metadata. And we've taken all the metadata out, and that's the index node. And that was a linked list of index nodes. Then we've taken that to the next level. Now it's just, well, it's basically our understanding is just improving, like to the next level. Our understanding is just getting better.
Okay.
So now we've taken these index nodes and realized, hey, we know we only have 4 million tables. It's okay, it's 200 kilobytes of overhead or 400, 500 across the whole forest. Let's just allocate all of these all this metadata contiguously, because we're going to get much, much better performance. So it's
Hey,
going to be pretty amazing.
Omar asked if you can like make my screen bigger on the Discord call,
Yeah, sure.
so that they can see better on stream.
Okay, cool. There
Cool.
we go. Thanks,
Thanks.
Omar. Yeah, I was just, yeah. And then I guess there's one thing. Okay, so two questions. I was just wondering yesterday, like you said, we're going to make it a slice of index nodes because we don't want to allocate this on the stack. We want to keep allocating because we're thinking this is like 500
Yeah, we don't
kilobytes.
want
So
200 kilobytes
we don't
in
want such a big
inline disk
structure.
space.
Yeah.
Yeah.
So definitely we're going to allocate it. And then the other question was, or just a thought, like our Eytzinger layout, we kind of haven't worked out the static allocation for that. Um,
Oh no, we haven't done that.
yeah,
But we can kind of make that however big or small we want it to be. Um, so we should probably do that though to just kind of get a ballpark estimate on how big would make sense.
yeah,
Um,
and just check that we don't
and
have a
given the
showstopper
market
there.
for a similar amount of memory though, like a couple hundred, like 100 kilobytes or 200 kilobytes per tree, I think would give us a quite significant speed up.
Yeah,
And beyond that point, Eytzinger can help less actually because then even inside the Eytzinger layout, the keys are farther apart.
yeah.
Um,
It does still have the advantage even there where you can prefetch the great grandchildren. So even if they're further apart, it's not a problem because you can prefetch them
right,
all
right.
16 in one.
It's still better. It's just the trade-off becomes less extreme. It becomes
Yeah,
less
yeah,
obviously better.
yeah,
I think that's also why prefetching isn't helping us on our other Eytzinger layout benchmark because we only use the Eytzinger layout for the top level of the tree, not for the end. And for the Eytzinger, the prefetching really helps mainly for like the actual the very root of the very leaves of the tree.
as the
We can then
Eytzinger
get like a
gets
block of
big.
contiguous nodes again.
Yeah, exactly. Yeah,
Um,
yeah, yeah. So we need something I was thinking too, Isaac. Maybe we're calling it level manifest. Maybe it's better if we flip it around and actually call it manifest level, because then we're going to have a bigger
sure,
structure outside of this just called manifest, which will comprise of like these. So
that makes sense.
yeah, yeah,
I'll
something I
rename the
like.
file too when we're done.
Yeah, yeah,
Right now it's called level tree, which is outdated by a couple iterations now.
yeah, cool. And then, um, so we're going to have like one manifest over all of this, maybe on top, or we can see. And then
Yep, it'll just dispatch to the different levels and
per
do
level.
that. Yeah.
Yeah. And then the other question is, or just an idea is, or something to think about for, I was wondering, like, I was just asking the question, can we do this icing allowed actually across all the levels? Like, do we get to a place where it makes sense? Like, given a key, just find me the first table in any level where it's at. Um,
I don't think so, no, because the levels have overlap between each other.
yeah.
I think you also can't delete your layout for level 0 because of the overlap, at least.
So I was wondering, like, what if we have like a Uber precedence function that can sort that all out? So everything
Hmm.
is just.
What do you, well,
But then I realized it wouldn't work. It could work maybe for queries, but it wouldn't be great for compaction because compaction we actually need to know like at, maybe we must just keep going like this. But this was just
I think,
like a long range, just
yeah, I'm
a
not
what
sure that
if
works out
question.
well
Yeah.
because the Eytzinger layout doesn't really give you, it seems like your things are backed in one contiguous linear storage of some kind and gives you an index into that storage. But if you have got like if you're trying to do it across like many different storages, then if you're still gonna index to just like having you
So
I don't know. I think
what I
it
was thinking
doesn't. I think you
was
don't gain anything by doing that. Is a problem. I think that's
yeah,
the main difference.
the,
You have
the
to like make these.
the gain would be like normally with the LSM trees have read amplification because you have to check each level and go down and check all the trees at each level.
Yeah.
So you've got multiple branches each time you're checking a level. It's basic. That's the read amplification cost. All the bookkeeping overhead. Doing it would there would be an advantage if you only had to check one thing and it just does it all with
I don't
single
think it
branches
works
at there.
though because Yeah, so the problem is like with our if we had like an Uber precedence function, which said that if keys match, then take the key from the higher table
Yeah,
or the table up higher up in the tree, and then but you also then end up with a lower key, like in the key sort order that's lower down the tree and doesn't have any key higher in the tree. Then you've got like if you're doing your indexing based on like 1, 2, 3, 4, and then just like having indexes in between in trees, because like the Eytzinger needs like some contiguous way to map the indexes across all the levels to a contiguous or flat array.
yeah,
Otherwise, the results doesn't make sense.
yeah,
Then you get stuff that's out of order.
yeah,
Um, and so you have to
exactly.
then basically say that all things at a level come after all things in the level above. And then you've just made your Eytzinger layout much bigger for, yeah, I don't know. It doesn't seem like it would actually be beneficial to me.
Yeah,
And I think it'd also just be a lot more complex without any benefit then.
yeah.
Um,
I actually thought it could be much simpler and faster. It's just that I don't think it it was just a question. Like it's just wondering, like, what if we did this?
yeah,
Because the idea is to throw away a lot of per level code and just have one thing that just does everything. But the reason why I don't think it would work is because I think if it could work, it would be fantastic. But I don't think it
yeah, I'll agree
could,
with you there.
yeah, I don't think it could work for the reason you gave, because the Eitzinger needs the data to be in sort order.
Yeah,
So we would need to do, like, if we run with it, like, I'm not saying we should do it, I'm just wondering,
okay.
like, our precedence function, we would need to have the I don't even know. I just don't know if it's possible. Like our precedence function would make, there would be a sort order.
So the data wouldn't be, yeah, I think the data wouldn't be in that order though. Like you can make a sort order over this stuff, but the data wouldn't be laid out in that order on disk, so you couldn't efficiently index into it then with the with the results of the Eitzinger layout.
Yeah.
Um,
So
because I'm
it's
pretty sure.
it's it's just the, like, for a point lookup, find the table that we need across all levels, like just to solve that problem. So what if we had precedence function, the most significant bit is the level, and or maybe the only thing that matters is the key. If the keys are equal, then it's the level.
Yeah, but then you get stuff that's out of order if you have keys that aren't does that don't happen to be on different levels. That's out of the order they are on disk, I mean. And
Yeah.
also if you like have yeah,
So the only
I think it
if
just
we
doesn't work.
if we ignore disk, the only thing the only thing that this manifest has to do, that like the sole problem we want to solve is, for example, for a point, there's two jobs. For a point lookup, find the table that this could be in. That's all it has to do. Just find the table info.
Yeah.
That's so it's actually decoupled from disk. It's just get the
That's a good
fastest
point.
way to get the table info for this key and snapshot across all levels.
And so we could just then return essentially maintain one massive sorted
Unrolled
um,
linked list.
list of table infos instead of one per level. And
Exactly.
then we would sort it by um, I guess first by we need to store the level then in the table infos is the thing.
Yeah.
That's the main overhead of this. Do you have a place we can
That's
stick that already?
yeah, if
Um,
it's not a problem, because that's just a little bit of memory overhead, but
that's a lot
the
of memory overhead if we've got like 4 million tables.
yeah,
Um,
yeah. But that's okay. Like if it makes queries faster, it's fine.
okay. So right now we've got like this stuff. Checksum address, timestamp, keymin, keymax.
Yeah.
This we can't use. Address. we can probably take like some bits from there, to be honest, because we already we think we only need 32 actually, but we could probably definitely get by with like,
Yeah,
um, what do we need for a 7 integers? That's only like 4 of the bits, right?
yeah,
Yeah, so we could get by with 60 bits, I'm sure there, and take 4 bits for the level.
yeah,
Um, timestamp, we need all the bits there, because we already have taken one away for tombstones.
yeah.
Um,
So we
then we've
wouldn't,
got one,
yeah,
yeah,
we could actually do it without adding overhead for the level. We just steal a few bits from the top of the address. That's fine.
yeah,
But, I'm just wondering. I'm not saying whether we should.
yeah. I think this is worth pursuing. I'm getting more convinced.
Okay,
Um,
cool. Yeah, and I'm not even
because I
trying to
realize that,
convince you. I'm just wondering. I'm just asking the question, like, if we did it this way, could we make it work? And then we can evaluate it, like, what would be the pros and cons? Do we want to actually do it? So we're not yet
I think
at the do, but like,
yeah,
just how would we do it if we did it? And not whether it's a good
I'm now
idea.
convinced that we can make it work, but I'm not sure if it's better or not. And
Yeah.
so we basically just have one contiguous array that happens to contain table info from all levels. And each table info stores what level it's in. And so then your sort function for this array is then based on first the key min and then the level. With lower levels, like level 0 comes first in the array. Level 0 may need special handling because of the overlap. I'm not sure.
So that would
But
be the
yeah,
timestamp coming into precedence as well. So if they're both at level 0, then the table
yeah,
with the higher timestamp will have higher precedence.
yeah. So then you get the overlap properly,
Yeah,
and then you just literally scan until you find the first thing,
yeah,
which is what the Eytzinger layout does for us essentially.
yeah,
Um, seeming kind of attractive. And I think we'd also then actually reduce overhead in terms of memory
exactly.
from these buffers because we don't need 7 of them. We only need one of these, and it's the same
Ex
size, I think, because yeah.
exactly. That's
So
what I
that's
was
quite
thinking
nice.
too. Yeah,
Cut that overhead in 7, then we have got a lot of memory to use for the Eytzinger layout, and so we can make that really big.
yeah,
Um,
yeah.
hmm,
And and the so I just thought it seems simpler because we just instead of having an iteration across 7 levels, we just query one Eitzinger and
yeah,
one, and it's an easy
iterate across
mental
one level.
model. Yeah,
Yeah. It also sounds really nice for range queries because you don't need to do a k-way merge then. You just iterate over one thing, which
yeah,
has all your data in the record already.
yeah.
Um,
Because that's what I was wondering. Can we make it like, is it possible to like, how could we make it work? Like for range queries and for compaction, because compaction, we want to know, I've picked this table at level A. Now, manifest, please, would you give me all the tables at level B that overlap? So would
yeah.
this design work
And
for that?
so how does that work then? Um, yeah, so if you say we pick this table at level A, then you've got a key min for this table, and then I think you kind of need a separate API that does this kind of query. Because it'll already be in the sorted order, but what you want to do is like skip the ones at level A until or at all levels before you get to level B
Yeah,
when you're searching. So
yeah,
you need like a different comparison function for this search, but the tables are still in the right order, or
yeah,
you need like a different equality function maybe. I think that
yeah,
can work out though. Um,
yeah,
Eitzinger layout won't get you to the exact right place though, I don't think. Well, or no,
yeah,
you just search by like I think you just like you kind of build a different key. Um, that takes. I think we might want to just like have different keys for the sort and and then we can search by a key that includes the level as well as the key min. Um,
yeah,
and then when you want to query all the tables at a level, you're gonna construct a key that uses the key min and the level you want to search for. Then throw that at Eitzinger. You'll get back an index where you can then start your backup binary search, I guess.
yeah. So In other words, are you saying we have two Eytzingers, one where you shard per level, and one where it's keys in sort order across the whole tree?
Yeah, essentially, I guess.
Yeah.
And so we have one Eytzinger where it's just keys in sort order across the whole tree, which works great for range queries and point lookups. And the other one where the keys are also, they're actually not equal. Well, maybe we just need one then.
What I'm thinking is
Hmm.
if we just have one, the keys are essentially they're going to be sorted by keyman,
Yep.
and it's only keys that are equal where we will then sort by table and by timestamp.
Right.
Otherwise, all the keys, the table infos are going to be sorted according to key min. So, so what's going to happen is we're going to have the levels all over the show. It'll be like sparse. So
Yep.
we'll have to iterate across the whole unrolled linked list to when we do a compaction to gather all the things that could, well, not kind of like we can kind of do both. We can use the Eytzinger to get us to the first table info
Right.
where the key
We get,
min,
yeah.
and from there we can then iterate in our unrolled linked list, which
Yep.
should be pretty fast.
And we can also know when we're done during the iteration. Yeah.
Yeah,
We don't, because we'll see like a key that's greater than our end key.
yeah,
I think that's fine. It's just it makes the iteration need to skip over. Like I think the main downside for compaction is that then have like extra data skip over during iteration. It's not on the
yeah,
level you're iterating.
yeah.
That's the
But
overhead. Uh,
yeah, and that's okay
is
because
that going to
it's
be
not
significant? Like if you're iterating
as
a low level, a lot more data at or if you're iterating like level one, there's not going to be that much data on level one, so you're probably gonna have to skip over a lot of data from like level 7 because you grow at a factor of 10 for each level, right? And
yeah,
so
yeah,
level 7 will be like thousands of times larger than level 1.
yeah. That's true. So
And
we
so for level
will,
7 it'll be almost no overhead, but for level 1 it'll be quite a bit of overhead actually, I think. Um,
yeah. On the one hand, like just throwing it in there, like compaction, whenever we compact, we have to recreate the Eytzinger layout anyway,
hmm.
because each time we add tables, we rebuild the Eytzinger layout.
Yeah, because we might insert stuff in the middle, right? Yeah.
Yeah, but we only, okay, that was the one thing we realized yesterday. We only rebuild the Eytzinger layout if we change, if we add a unrolled node, or if we change the key for that node. That's the only time we have to change the Eytzinger. So that's, so we don't
Oh,
actually,
well, I'm not sure. I'm not sure I followed you there. Is that
yeah.
are you saying that the Eytzinger layer would only give us like the index node, not the actual data node, or it would only give us the data node, or if it's giving us actual indexes to the table infos, then we do need to update the Eytzinger layout.
So yeah,
Um,
so I was thinking of index node and data node. They're actually just one node because a node has metadata and data. So
okay.
the Eytzinger is actually just going to give us the key min of a data node.
It's gonna give us a data node. It's not gonna give us a key min. It's gonna give us it returns like an index, right?
Yeah,
And I'm just
yeah,
asking what does that index mean?
yeah,
Um,
yeah. But the value is the data node, and the key will be the precedence key, which is key min of the data
okay, so
node.
it'll take you to a data node then. The index
Yeah,
will be the index of a data node across the whole tree.
yeah.
Okay, and so you don't need to update the Eytzinger layout unless you've like run out of space
Changed.
in the data node and had to create a new one.
Yeah. If we've inserted one, or if we have changed the first key in the inner node.
Yeah. I think that's kind of like orthogonal to like the potential showstopper with compaction being really slow for level one. Um,
Exactly. No, no, I know. It's just an extra data point. So
yeah.
the idea is that we don't have to it, we don't have to always rebuild the Eytzinger layout when we do compaction. We only have to rebuild it if we're inserting new data nodes or changing the the key min for a data node. That so we don't just the idea is that Eytzinger layout rebuilding is decoupled from compaction. It happens every few compactions, not after every compaction. Uh, it's
Yeah.
just that, yeah,
And
that's one point.
yeah.
Then there's the point we're discussing, like the overhead when we're compacting level zero, find all the overlapping tables. We've got to cover quite a lot of ground in our unrolled linked list. We've got to iterate. I'm I'm just the reason why I bring up the Eitzinger rebuild cost is because it's kind of related. Like if we're doing a compaction and we have to find tables anyway, if we do the compaction, we have to rebuild the Eitzinger layout. But okay, we've realized we don't always do it. The other thing too is with compaction, compaction isn't the common case. So the most important is read queries, range queries. Want those to be like super fast.
Okay.
So compaction is now and then, and it has a bit of overhead at the start when it iterates to find tables, and it has overhead at the end when it maybe rebuilds the Eitzinger. But it's okay if
Yeah.
compaction. The other thing too is we sharding, so this worst case is going to affect like 3 or 4 big trees, or maybe 2. Um,
Mm. Yeah. I'm kind of becoming less convinced this is a good idea versus having a different like our current approach of having like a level manifest per level
yeah,
or a manifest level thing with one
yeah,
icing layout per level, and then the compaction is no problem. That makes things much quicker there.
for
And you also have
compaction,
to like
yeah,
Eytzinger layout also becomes very expensive to build, I think, if you've got it across all levels of all trees. Um, because you're not going to be touching the lowest level very often. You're not going to be inserting stuff there very often, I don't think.
yeah,
And that one makes things a lot more exponentially more expensive to rebuild because it increases the number of data across the whole tree by a power of 10 or each or factor of 10 each level.
yeah,
And so the bottom one's very expensive to rebuild the Eytzinger layout for. The top ones are much less expensive, and so if you don't need to do the bottom one, then that's great.
yeah,
Um,
yeah, exactly.
I'm
Now, I was also
thinking we
thinking
want to
that,
split this across trees so that we get that like nice pattern where we have less overhead for the lower levels because they don't have this massive, um,
yeah,
they aren't as
yeah.
thick as the bottom level.
So we want to
Um,
have like we want to keep our Eitzinger per level. Um,
I think so. I think it
yeah,
makes things simpler too. I think the other
yeah,
approach is actually a lot more complex. Even though it's only one data structure, I think it's just a lot more complex because of you're trying to do everything on the same thing across all levels instead of just across one level.
yeah,
And so you like add another dimension to that, which is like what level the data is on.
yeah.
Um,
It's also complex where it's basically just when we do compaction and we have to find tables, we just need a little extra iterator that can skip over. But I mean, it does have a big advantage for reads and range queries because it's just one thing instead of
yeah,
multiplied by levels,
maybe there's another data layout besides like a contiguous list then we can employ there, make the compaction iteration quicker somehow. Um, I don't think that works out with Eitzinger layout then, is the problem.
Yeah,
Because you still need
yeah,
the linear ordered, um, not array, but just list of
yeah,
items that you want Eitzinger layout look up.
yeah. Yeah, so on the one hand, compaction is not the common case. So the lookups don't have to be fast, like finding the overlapping tables can be a bit slower, but it seems like it's going to be quite slow, and rebuilding our Eitzinger across all levels is going to be much slower.
Yeah, those both becomes like powers of like hundreds of times slower um, than they would be if you only had to do it for level 1 or level
Yeah,
2, for example. Um, I think it's probably not good.
but when we do it for the bottom level, it's going to be essentially the same either way.
Yeah, but we won't do that as often.
Yeah,
It'll still be a little bit slower, but it'll still be like faster than it would be if we did it for the whole tree at once, because the bottom level it has only a little bit more than half the nodes, I think. I remember if I did the math
it,
correctly in my head.
it'll have
Um,
90%, like almost.
okay, that's I was way off then.
Yeah,
Um,
the because
yeah, that makes
because it's a
sense. Yeah,
power
but
of
it's like like
factor
80
of
something
10.
percent. Yeah, yeah.
Yeah, almost all the tables are in the bottom level, either
Well,
way.
if it's full, but it's not usually full. Um,
Yeah, exactly. Yeah, but
and
if it
so
isn't full, then either approach is fine because there's no overhead anyway. Um,
well, if it's like, I think we probably want to optimize for the case where it's like 70% full or something like that. In which
yeah,
case, you do have a lot of tables in the bottom level.
yeah,
'Cause that's like a reasonable usage case where then the number of tables really starts to matter, but we
yeah,
still want to keep operating at high speed.
exactly.
Um,
Yeah, yeah. So that's also interesting because we want it to be scalable, not slow down when the tree is like more than 70% full. So almost all the tables are in the bottom level. So we're gonna, I think maybe, what do you think? Shall we like work out, like, let's just say we're gonna do this per level and then work out what size Eitzinger we need, how our static allocation for
sure, let's
Eitzinger
do
will
that.
work. Because once we know how much memory we need, we can have an idea roughly of how long it'll take to construct. And then we can
Sure,
just
yeah.
see how it will work for the bottom level.
Okay, and so are we gonna do Eitzinger like or what's our value in terms of the Eitzinger layout lookup? Is this the table info or the data node? Um, it
If
doesn't really
if
matter. We can just make it that. So that's kind of a question of how often we will rebuild it. Really,
exactly, yeah,
if we make it the data node, we have to rebuild it less often.
yeah.
Um,
If we make the Eitzinger just the data node, then we're gonna go through the Eitzinger, very nice memory access. Then we're gonna jump to the data node, and then we're gonna do a little scan there also.
or binary search, or
Binary
maybe it
search.
scans faster at that size. I'm not sure.
But yeah, binary search will probably be faster because the scan will
I think
only
so.
work
Yeah.
if it's a cache line, but beyond that, binary search. So we'll do binary search
Cool.
there. So probably then we want the Eitzinger to index the data node, not the table info, because then we don't rebuild Eitzinger as often.
Yeah, because I think that's the main trade-off because we could access that's unless we want our itinerary to be very large and then we have more memory than we need to index all the data nodes, and then we end up getting worse results because we're only indexing data nodes instead of the finer granularity. But I think we
Yeah,
don't want our
yeah,
itinerary to be that large. I think indexing the data nodes is like a good middle ground between like itinerary
yeah,
layout size and then being useful to skip comparisons and jump right to where we want to go.
yeah.
Um,
And it's very nice if we only rebuild Eitzinger, if Eitzinger indexes the data node, not the individual table infos, we gain a lot because we don't have to rebuild Eitzinger, which really helps us for the big low level.
yeah. Hmm. I'm thinking more about how we want to do this layout to make index lookups faster. I just kind of thought where we probably maybe want to take the elements total out of this index node and have like a slice of those. Kind of how we did with this same approach, like have only like one buffer of elements total, so then you can like skip the nodes without even looking at them, without even chasing the pointers there. Um,
Yeah,
that can be. We can talk about that later, though. I think that would be a good idea.
I was wondering, like, why I've if we have the Eytzinger as an index to data nodes, do we even need the index nodes as much? Like, the index nodes are great if you want to iterate across data nodes. Like, if you want to
we
get a data node
we
that
still need to find the
contains the
data node.
element at
So we need to go from
index I.
index to data node. And so there's
Yeah,
no, if you just have a linked list, then there's no way to get there besides iterating. And
yeah,
so you need an index node to be able to jump there.
yeah. So we need it for the iterator. That's the point there.
Well, we need it just for everything. If we want to do the Eytzinger gives us an index out. To get from an index to a data node, we need to then, if we didn't have these index nodes, we would have to then iterate the full list of data nodes to
Yeah,
find the data node we want.
yeah. But what I was wondering is, Eytzinger, there's nothing stopping Eytzinger from having a pointer to the data node.
Well, it just makes our Eytzinger layout bigger and slower. Right now, we only store keys in the Eytzinger layout, not the actual values.
Of course. Okay. Okay. But I mean, whether we have it there or yeah. Okay. Because I mean, if we store a pointer there, okay, we're gonna get the index out comp time from Eytzinger when we do the search. Yeah. Okay. Now I'm with you now. And then
All right,
I'm
cool.
I'm just double checking just to load everything up into RAM,
Sure.
into cache. So that we also need the index nodes for iteration, where you've got a table info and now you want to move, or you've got a table you want to move and iterate by index. That's why we need, yeah,
You need to link it between the data nodes somehow.
yeah,
And so you can either do that with linked list on the data node level, which would be kind of slow, because then you've got a lot of pointer chasing,
yeah,
or with the index nodes where you have a lot bit less pointer chasing.
yeah, exactly,
Um,
yeah. And but the binary search idea we had on index nodes yesterday, what were we thinking to use that for? We weren't really going to
um,
do that, yeah.
well, you need to fall back from Eytzinger to binary search, essentially. Like, Eytzinger will only get you so far.
But
It
I,
won't give you an exact
eh,
location.
okay, Eitzinger is going to give us. Oh, this is actually it. So Eitzinger is going to give us the. Because I mean, it's also up to us, like we can do one for one. I was actually
We
thinking
could.
Eitzinger indexes all the data nodes, not just a subset.
We can see how that works out. We should look at how much memory we would need for that.
Yeah,
Um, if we do that, that might be nice. Then we could then maybe do make some different decisions here,
that's what
and
I
just
was
optimize
thinking.
this for iteration instead of point lookups. Um, if we can somehow jump to a index node or data node from that, which also is not trivial. Yeah, we still need to be able to jump to a. We still need. I think it's still going to give us an index, even if we don't use the binary search on these things. We need a quick way to go from index to um, data node, essentially, or data node index to data node, which means that we need to iterate over the index nodes and
Yeah,
add up elements total.
exactly.
Um,
So we
yeah,
want all of this for iteration, but we can use the Eitzinger for finding a data node, and then we can binary search within that data node.
yeah,
And then we'll use, if we need to iterate, having found a table info in a data node, then we want to iterate further outside of the data node into other data nodes, then we'll use our index node.
yep, something like that.
Yeah. So we're not really looking at the index node, the contiguous slice of index node metadata. We're not really thinking of that to do binary search because we can do that in the Eitzinger. Like to do binary search across data nodes, that we can do at the Eitzinger level. The index is there just
Yeah.
to support horizontal
Well, we
iteration.
think we can. We need to figure out how much memory it will take first.
Exactly, yeah.
Um,
Yeah.
Yeah. Eytzinger layout will store like one key per table info essentially. It'll
Uh,
store the key min
just per data node.
or per data node. Yeah.
Yeah.
And so data node, when we have this data node element count, let's get Python out, I guess.
Yep.
So
One data node has like 340 or 320 table infos.
the keys per node equals 4096 divided by 96. Is 96 our table info size we're going with for now?
We should actually use 64 because the distribution will skew towards 48 or 64.
Okay. And now we're going to take keys per node. Well, just first of all, that is 64 keys per node then. Then we're going to divide our 4 million number. We have our thing is like 4 max equals 4 times 24 times 24. And so tables max keys per node. That'll give us that many keys in the Eytzinger layout times the key size, which is going to be that times key size is our number of bytes for the Eytzinger layout.
I think
That's,
it's actually Eytzinger layout has one key per node. Okay, tables
yeah.
max.
So this is the number of nodes here.
Okay, nodes. Yeah, nodes.
And so if you have one key per node in the Eytzinger layout, then
Yeah.
yeah, we can here say then node
Yeah.
count equals
Cool.
that.
And then that's basically the number of keys in our Eytzinger layout, like you said.
Yep. And
Yeah.
so size equals node count times key size. So it's going to be, oh, if we have a 64 byte table info. What was key size? Was that 32 byte? No, that's a 16 byte key size, I think.
Yeah,
Or
on
16-bit
average,
key size.
our keys will be um, they'll be like 8 bytes or six,
I think 16 is what we do.
16
Oh, we get us at 64
to get
here.
that. Yeah, 16. Cool.
So that's pretty big. That's 1,000 kilobytes. Can't we make this a lot smaller though for the bottom levels? Like we're gonna have a cap on level size, right? I feel like we should divide this or make this based on the level size.
Yeah,
Like the maximum level size, I guess. So it'd be
because we
what?
we do we do know like we do have a cap and we can literally do
Yeah.
divided by 10 because we know like yeah exactly.
And so um so level for each level, the level size is going to be something like tables max divided by whoops, divided by 10 times level, right? Or no, it's gonna be like
Yeah,
yeah, 10 times level, or
it's to
that's
the
like
power.
that's like the inverse of that. So it's gonna be like
It's
7 minus level.
I think it's to the power of we need to bring something like that in level. Um,
Oh, 10 to the power of level. 10 to the power of 7 minus level. So then for level 7, you get
0.
a 0 here.
which
So
will
10 to
be
the 0 is 1 though. So that
is
should actually
1.
be 6 minus level or something.
Yeah.
Yeah, level equals, I don't know, 7. And if we do it for level 5, for example, then it's like, is this right? That seems like too big.
No, it's actually, you're right. You had it right, I think. 7 minus the
I had it
level.
right.
So basically, this is showing you like, it's basically saying in the bottom level, we could have all tables could be there. That's possible, which is tables max. So the bottom level has tables
Yep.
max, and then level 6 is going to have 7 minus 6. It's
Yeah.
7 minus 6, yeah.
Get rid of this level variable. It's not helping. Then we got 7 minus 5.
For
Yeah.
And then shall we go all the way up to level 0 just to check where that ends up? 3, 2.
We got 0 tables at level 0.
Yeah, the reason is because we've gone for tables max of 4 million. So what this is actually showing us is that for 4 million tables, we don't really expect to get into level 7 in the first place. We're not going to
No,
need
we actually
7
don't think so.
levels. Yeah. So actually
So
we can
we
get
instead
away
start
with,
start at level 0 and then do like level 0 is at 10 tables.
yeah,
I think it's the plan, right?
do it that way, yeah.
Then
And that
plus
we can
100
limit as
tables at
well.
level. Hmm?
Yeah, that's it. What you're doing now.
That's level. So it's just so at table 7 we've got 10 to the 7th tables, right?
Yeah.
And so it's not. That seems wrong. That's 10 million instead of 1 million.
No,
No, 10. That seems right. Yeah,
that's right.
that's the
It's
maximum.
Yeah, you see, we've set our levels max at 7 just to make sure that we will always have enough levels. But what all of this is saying is that we're never really going to fill up the last level. We're not with tables
Okay.
max of 4 million, we're never really going to be full in level 7.
Okay. And so what we want is to see like this minus. So let's see how many tables we fit in all the other levels. That's gonna be we're gonna fit like a 1 million. This is 10 million, right?
Yeah,
Yeah, and so that means level 6 is 1 million. We have 1 million, and this is the number of tables. Tables 1 to 6 is 1,111,000. This is a 10 then at the end.
yeah,
And then if we take our tables max minus this, we'll get the number of tables in the last level.
yeah,
That's gonna be 4 or tables max minus table 1 to 6. That's gonna be the number of tables in the last level. So that's our biggest Eytzinger layout now. It's 3 million keys only.
Do we have like a unit swap where it seems like we've done binary in 11110 and then we've gone to base 10.
That's not binary. No.
Okay. Of
That's
course,
the
it's 10 plus 100 plus 1,000, 10,000. Yeah. Each.
exactly, yeah.
Yeah, perfect. Okay.
So it's tables 1 to 6. And then we got take tables max minus that number, then you get this number.
Yeah.
Um,
Perfect. Yeah, great.
tables max is also probably too big. But yeah, that's only 3 million tables. And so we then take, well, let's see, do I have we do this? Now we got 3 million tables. Well, table or level 7 tables. is that, and then we continue to take multiply that by key size, and we'll divide that by the
Data nodes,
well 7 tables divided by
keys per
keys
node
per node, and then
times
multiply
key
that
size.
by key size
Yeah.
times 16. That's gonna give us
7
750 kilobytes for the last level.
of
Um,
of all trees.
yeah,
But also, what's good is that we should probably work this out for level 6.
yeah. So level 6, it's gonna be then just 1 million.
Yeah.
Um, um, sorry, I'll get the kilobytes a little bit more readable. 244 kilobytes. Yeah,
Yeah.
level 6. And then for
So we
5, it's gonna be
24 kilobytes. Yeah.
yeah, exactly.
Cool. So we for level 6, Isaac, we're looking at like say 30 trees times 244. What is
Sorry,
that?
in 30 trees. Yeah, so
Yeah.
sorry, 30.
Yeah.
Yeah, that's 7,327
So it's basically 7
megabytes.
7 megs. So that's okay for the whole forest.
Yeah. And also, I'm realizing that for tree levels below um level 6, we maybe could just get away with a contiguous array instead of doing linked list stuff.
Yeah.
I think we should statically allocate contiguous arrays for levels below 6, I think. That makes the Eytzinger then way faster. Because there's no
Yeah.
more linked list nonsense.
Yeah.
Um,
The Yeah, that's cool. Then we don't even worry about pool allocation.
for those levels, we don't know.
Yeah,
The pool allocation is only for the big levels, level 6 and 7.
yeah,
Um, for level 5, which it's only 24. Well, so it's only 100,000 tables. Maybe we still do that for level 5, for level 4 and below. But then we definitely and then 10,000 table infos
yeah,
is not very much. That's 10,000 times 64
yeah,
bytes. So it's only 64 kilobytes. But then we just make
yeah,
our pool allocator a bit smaller, or
yeah.
give that a bit less memory.
Awesome. That's a great idea. You know what I thought too? We must goal seek on tables max so that we only ever have 6 levels and we set levels max to 6. So we only have one big level, level 6. We don't have a level 7.
Okay. And do we make level 6 then like just grow? We just make level 6 arbitrarily large then, or is that the idea?
We can't because level 6 has to be limited by tables max because we're only going to have so much static
Okay,
allocation.
right, but we make it
Yeah.
grow by potentially more than the factor of 10.
Uh,
5.
what are our level 6 tables count?
It's 1
It's
million.
okay. Yeah, that's not enough.
Can we not make it grow than more than a factor of 10? Or is that not a thing you can do? Um,
Yeah, like the growth factor between levels.
you not increase that for level 6, or do we not want to do that?
I think we can. Uh,
It'd definitely
it
be
need.
nice to only have like one level with a variable size,
Mm,
like pool thing.
mm. That's what I was thinking. Like,
But if we have the code implemented, we can probably just use it twice. It shouldn't be too hard to like just use it for 2 levels instead of just one.
yeah,
It's more like just like some glue
yeah,
code
it's
in
fine.
the actual manifest. Like we
Yeah,
shouldn't restrict our design to try and make it so there's only one. We're already gonna have 2 different kinds, and that's like the big step. And so deciding which levels get which kinds is more of like a
yeah,
just change a few constants um,
yeah.
kind of thing instead of Yeah.
Yeah, that's better. That is true. Uh, yeah, a million tables times 64 is it's like 64 terabytes
Yeah.
of total addressable storage.
64 megabytes, right?
Mm,
We're talking about like maximum storage size now. This is in megabytes. This is now going to be in kilobytes.
yeah,
No, that was the wrong direction. Um, we wanted to go to terabytes. This is now in gigabytes, and
yeah,
now this is in terabytes. Yeah, 61
yeah,
terabytes.
yeah. Because you know what we could do is we could we don't have to change the growth factor. We could increase the max table size to 128 megs
Hmm.
and do
I think
that
all our
way.
code works for that still. Yeah, and then you get 100 gigabytes,
Yeah.
120. Yeah.
And that way
Hmm.
we only have to have 6 levels.
Right. And once the tables are in the last level, they won't get further compacted anyways.
They will be compacted with each other. Um,
Okay.
to I'm not sure or just they will be like compacted just to drop tombstones or I don't there is
Something like
something
that.
where you
Yeah.
have to do a special compaction in the last level.
Hmm.
We have kind of increased our growth factor though because we've just
Now then
increased
you
it
have
for
to
the
have the
last
tables
level.
in the level before this larger. Um,
Sorry, Isaac?
I think the tables in level 5 then also have to be larger. They've got to be then like think, right?
No, they don't have to be. They can be 64 megs at level 5.
Yeah. But before they would only have to have been 32, I think.
Yeah. No, yeah, it doesn't really matter. But we
Okay.
do by increasing the size of the table in the last level, it's kind of another way of just increasing the growth factor in the just for the last level.
Yeah.
It doesn't. It means that if you do a compaction from 5 to 6, you'll read in 64 megs and read in 128. So they're not aligned like that. So you are
Yeah.
reading in a bit extra. So it's the same as if we had a bigger a, a 20 growth factor. Yeah, in the last. I think it does make sense. Like if we know what level, yeah, to relate like tables max to the level somehow, but maybe we don't have to worry about it. And I think it's a great idea where we say, let's do just static allocation for contiguous allocation for the small levels and just 6 and
Yep.
upwards we do
Cool.
pool allocator.
And so it depends where the trade-off starts, because with the contiguous allocation, we then still need to like we'll need to insert table infos into the middle then to maintain sort order, which means you gotta do a mem copy then to shift the data,
Yeah,
make a free slot, which is totally fine for level 0, for example. But there's some
yeah,
point that becomes expensive.
yeah,
I'm not sure where that point is then. Um,
yeah. So level 5 will have 100,000 tables times 64
yep.
is going to be 6 megabytes, which will be, we can do 6,000 megabytes of memory bandwidth per core for every 1,000 milliseconds. So 6 is a thousandth of that. So we'll be one millisecond to mem copy a table into level 5.
Okay, that's not too bad.
That's right, eh?
I think so.
Yeah.
I can check your math.
potentially we have to mem copy almost all of it.
Yeah. 64 bytes per table. Yeah, so it's 6 million kilobytes. So it's 6 megabytes, yeah.
Yeah. Yeah, that's in kilobytes now. And
Mm-hmm.
yeah, so it's six megs, and we can do 6 gigs a second, so 1 millisecond of mem copy, which is okay. Maybe we would say, well, 1 millisecond stall in the event loop is not great. So because our operation to do the state machine operations, the latency is like 10 milliseconds or 20. So if we have a one
Yeah.
millisecond spike relative to that, that's like quite a,
Yeah. I think we can probably get around with it somehow, though. Yeah. Not sure what the best way to do that would be. We either like make that trade-off, or only do that for levels below 4, and then it's really trivial. Then
that
it's
is fine.
just
Yeah,
then it's like only 10,000.
yeah,
So it's only 625 kilobytes. That's
yeah, that's
much less
fine.
than a millisecond. And
Yeah,
then maybe we just use the same data structure um for level 5, but with like a smaller static allocation probably. Um,
exactly. And then what is our allocation? Because like level 4 will have 10,000 tables times 64. So that is
yeah.
600 kilobytes.
Yep.
And then it's times 30 across all the trees. So 600 kilobytes times 30 is going to be 18 megs.
Yeah. Well, actually, we end up with this is also we subtract this from whatever we allocate for the pool allocator then, because this is then tables we don't or memory we don't need to be in the pool allocator for lower levels.
Yeah,
Because if we keep the same tables max, I mean,
yeah,
um, and so you can, yeah, it's we stick this much memory in kilobytes, so that's 20 megabytes across 30 LSM trees into the first 4 levels,
yeah,
and then the rest of it, then we take well, this is the number of tables now. It would be then 11 million. This is the memory for the last levels. There's not 11 million. It's just it's this. Then yeah, 11 million was right. If we have 7 levels still, do we want 7 levels there or just 6 levels? We haven't really decided there. Um,
If we have tables max of 2 million, we need 7 levels anyway. So I think
right.
we do need
I'm going
up
to
to
take our
7.
tables max of 4 million. What we had
Yeah, times
for
64
tables max. I think
bytes.
well minus 11,000 for
Hmm.
this thing. Um, is now like the tables in the levels with the linked list Eytzingers or linked list based storage
Yeah,
from the block pool or whatever we want to call it,
yeah,
the pool allocator.
yep,
Um, times 30, big number.
yeah, it's going to be big.
That's yet this is now megabytes. 7 gigabytes. That's way too big.
Yeah. Another way to approach it is to say, what's the,
Well,
because we know that most of the memory
this is
would
this
would
isn't times
be
30 though, because this is pool allocated. Um,
exactly.
this is
Yeah,
only this is 255 megabytes.
exactly. And another way to get there
Cool.
quicker is just to say tables max times 64, because tables max has almost all of the tables. So you'll end up at 256 if you do it that way, but you get to the same order.
Right, and we're gonna have some overhead then for like the stack allocation for these other trees as well.
Yeah.
Cool.
But I'm thinking So this is like, maybe that's too expensive to have tables max of 4 million because that's 256 megs of RAM.
Yeah. I'm not sure we even need 4 million. I think we were fine with 2 million, weren't we?
2 million, yeah. Yeah.
Let's just bring it back to 2 million with the
Yeah,
power of
that's,
2, like
yeah,
2 times 224 to the table's max.
yeah. It's
Yes, just
one
127 is much better.
or 128. Yeah,
Or well, if you get rid of this, then it's gonna be exactly 128.
exactly.
Yeah.
Yeah, yeah. That other one is kind of like rounding error. It doesn't,
Yeah,
that,
it's not. It's the same power.
yeah.
Yeah.
So one, because what I'm thinking is if our pool allocation is 128, and if we're not doing pool allocation for some levels, like if we have to do 18 megs across the whole tree, across the whole forest, it's actually becoming quite expensive relative to what we do for pool allocation.
So,
So,
how many megs across that? Across the whole forest, would you say?
like level
Oh,
4
we
was
didn't have.
18 megs across the whole forest if we did contiguous, if we
Really?
don't do pool allocation.
Oh, yeah, it is.
Yeah. So it's another, maybe that's a reason that we shouldn't even do it at level 4, only at like level 3 or
Yeah.
and for
For
the
level
others
3, it's
we,
coming. It's pretty cheap then.
yeah,
It also makes the memcopy latency even better.
even better,
Um,
yeah.
while like maintaining the nice fast speed level at the really small levels.
Yeah.
Then that's this is now kilobytes. 62 kilobytes times 30 is like it's 1 meg then, or
Yeah.
2 megs roughly across the whole tree, which
Ex
is totally fine. So
exactly, yeah.
cool. We should
Yeah.
write this stuff now, I guess. I think. Are you
Yeah.
happy with this strategy now?
Yeah,
Um,
yeah, exactly. We can even say like um, we- this is level 3. We've got level 0, level 1, and level 2. We should maybe even say, right, level 3, we still do pool allocation because we save 2 megs.
well, actually, this is level 2, I think. We've got level 0. I think I've forgotten that levels were 0 index or something.
Yeah,
Um,
okay.
they may have been a thing. So this is now because level 0 is this right? Is our big number right then?
Yeah, I'll
Let's come
check it
back to
out
that.
first. Level 0's got,
10 tables.
yeah,
Level 1's got 100 tables, and level
100.
2's got 1,000 tables.
Yeah, level 3's got
Um,
10,000.
400,000. Then 5's already got 1 million, and 6 has got 10 million. We don't need a 7th level then.
No. Okay, cool. Yeah,
We can opt one of the levels if you get rid of that 7th level for sure.
definitely.
Um,
5 has got 10, it's got 1,000 times 10 to the power of 6. You know what we could do is we could say our, our table limit in level 0 is 8 tables. Our growth factor is 8. That way at level 6 we end up at exactly 2 million tables as a power of 2.
that sounds nice. I like
Yeah.
powers of 2 more than I don't know where do these 10s come from. Is that level DB?
Yeah,
Um,
level DB. It's a
everyone
trade-off.
did copy.
Yeah, it's a trade-off between read and write amplification. If you have
Okay,
more, if you have a higher growth factor, you will get better read amplification. A lower growth factor, you will get worse read amplification.
for better write amplification.
A better write amplification. Yeah. So for us, it actually makes sense to go with a lower growth factor. We'll get better write amplification, which is what we really, really want.
So we can
And we
better keep up with the incoming data. Um,
exactly, and we actually already get better read amplification because we have a forest. So that counteracts like going from 10 to 8. Um,
cool. So I'm all for powers of two. I like powers
Yeah,
of two.
yeah, me
Um,
too. We need a
cool.
T-shirt. Yeah,
What's your favorite number?
yeah,
2 to the 64.
yeah. Cool.
Or just two. I think just two would be my favorite number. I don't know. It's also like the only even prime number, which is kind of cool. Um,
Wow, that's pretty cool. I've been reading Jack Reacher books, like trying to work through the whole series, and
oh yeah.
he's pretty cool because there's a book now, I think Bad Luck and Trouble. I'm reading. I just finished. So he's a numbers guy. Like he's always talking about prime. So someone deposits money in his bank account, and he knows that they're in distress because it's at 10:30. Like he just sees numbers, and it's amazing. Like it's incredible. Like he's working out primes. Like, and it's on every page, literally. Like he works out the distance between things, and he knows like what the fraction is. I must try and get an example, but it's just what we're talking about. Like,
Funny.
yeah. So his girlfriend even deposits some money, and he gets disappointed because she wasn't clever with how she worked the fractions and then he realizes, oh, she did it in two amounts, and she's making this message. One of them is a zip code, so he must come and visit. The other one is something else. You know, so
That's ridiculous. I like it
yeah,
though.
yeah,
Cool.
awesome.
So, shall we do tweak our constants, or
Yeah,
you know,
these are cool.
toss this over in different minutes
These are
over
good
there?
ideas to realize, like where the levels are smaller, we can have a different strategy. You know,
Yeah. I think that'll make it that make it even better performance for the smaller levels.
yeah,
I think it also kind of highlights why doing it all together for all the levels at once was not really the best approach. I think then you really negatively impact the smaller levels, which is where we're gonna have the most churn during
yeah,
compaction,
yeah,
and we're always gonna have to query them first. Um,
yeah. You see, because what I was actually wondering, this insight that we don't have to use pool allocation for all the levels. I'm also wondering if we can use that for this idea of doing one thing, like
like do one thing for half the levels for the first. Hmm.
because then it makes sense. Like you
Does
have
that what benefit does that get us then? Um,
better read amplification. So you see at the very top of the pyramid, if we have to do a linear scan when we compact to find overlapping tables, it's not a problem. Like that, it's so cheap. So that's a non-issue. And it means that instead of doing three Eytzinger searches and three binary searches as we do read, we only have to do one.
yeah,
So it accelerates it
yeah,
basically
and so
cuts our read
and
amp in
it's also
half.
not very expensive, right? Because like when we have what so for the first three levels, we then end up with like instead of 1,000 for the first 0, 1, and 2 is what it is. And we have 1,110. It's the only difference. So you just add 110. Yeah, I like this idea now. Cool.
Yeah.
Um,
So
yeah,
are we thinking the same, Isaac? Like for
we
for the top of the pyramid, we're not going to do pool allocation, and we're going to put all the levels into one thing
yeah we're gonna put like the levels 0, 1, and 2 all in the same buffer.
all
Like all
together.
the tables infos go in the
And
same buffer, but then sorted by level when you don't get to sort by key.
Exactly. And
Um,
we're going to have just one Eytzinger for all three levels, like a Uber
yep,
precedence. Do it all like that for that. And then for the bottom stuff, we keep it separate and we do pool allocation. So we've actually got two structures. We've got the cap of the pyramid,
yeah,
like the capstone, and then we've got the foundation. And we're going to do two
yep.
different structures for both.
I think the foundation's harder, so we should do that for one first.
Yeah.
Um,
Okay. But you're happy we're going to do the all-in-one Eitzinger for three levels, like
yeah,
just
I'm
for
I'm
very
happy with
fast
that.
queries.
Because then, like, yeah, well, I mean, it's still like a power of 10 different in the number of things you need to scan. Because like at level 0, if we didn't do this, we could actually just skip the Eitzinger and just do a linear scan over 10 table infos, which would be even faster.
Yeah, yeah.
Just
But
consider that for a sec. Um,
yeah, yeah. Are you also were you wondering, just so I understand what we're thinking about, the power of 10 cost for compaction where you need to find the overlapping tables by doing a full scan?
I'm more just thinking like, say you only consider level 0 right now.
Yeah,
If we didn't combine it with the levels 1 and 2, then we could just do a linear scan over 10 table infos and not do Eytzinger at all, and that would be even faster. And then we wouldn't have to deal with like the duplicate overlapping tables in the rest of them. Um,
for compaction.
or just like for in general for our search lookups, there would no longer be
Okay.
overlooking tables, and
Yeah.
that would be like a whole another dimension we can just ignore because we just special case level 0 with a linear scan.
Yeah,
Um,
if we did a linear scan there though, it would be 10 tables times 64 bytes, so it would be 10 cache lines. Whereas, and we might not
but
find the table
we can
info
put the
there.
keys all together. We can destructive arrays and have just
Yeah,
10 keys.
yeah,
If the keys are 8 bytes, then you fit 8 keys in a cache line,
yeah,
which is almost 10. I think it's
yeah.
still faster than Eytzinger.
The thing is though, like what you're looking like, let's say we're not thinking of compaction, we're just thinking of the search path, like you say. If the table isn't there, then we've got to drop to 2 and 3. Whereas the Eitzinger is fast because we're going to go straight to the data node regardless of the level.
Okay.
And
So you're
chances are
saying it would be cheaper, but on average it'd actually be more expensive because we're adding overhead to each search.
constant
Okay, I think
overhead
I buy.
of those 10 lines. Yeah.
Yeah. I liked the more than I was mainly thinking about that for the idea that we would then not have to care about tables overlapping anywhere else in this code because it only happens in
Okay.
level 0.
Yeah, yeah,
That was the
yeah,
other attractive thing for this idea for me. Um, Not sure how
yeah,
much that matters though. Like maybe it's not actually that hard to deal with, but maybe it gets kind of ugly. I'm not sure about that.
yeah,
It would kind of be nice to not have to special case that, or
yeah,
to just special case that here with a simple linear scan and then not worry about it.
yeah.
Um,
It would be because so like the complexity is really like if we've got two data types, then we it isn't complex because we've got neat abstractions. If they both have the same abstraction externally, then that's fine. It isn't. It's like level iterated, table iterated. It actually helps, you know. Plus, we
yeah,
get better performance, and it does help with complexity because separating the problems out, they have different scales. So, like the design
exactly. Yeah,
changes as your scale changes, you think of a new design. It's like Jeff Dean's own rule, like the factor of 10. You know, as you get 10 times bigger, you need a
yeah,
new design. So then it's
exactly
just
what
a
we're seeing here,
question
pretty much.
of like, do we want to do
Yeah,
2 or 3? Because we can do 3. I'm happy. Like we have all the same interface, and we say level 0 is this, level 2 and 3, 4, 5, 6,
yeah,
and I'm happy. We just go code it, and we all the same
yeah.
interface.
I think we should just go code that. I think that makes things a little bit simpler.
Yeah,
And then we can also it's also pretty easy to then combine level 0 and with levels 1 and 2 to then compare benchmarks to see if it actually hurts us to do that or something. Um,
yeah, yeah, exactly.
oh, maybe. But I think we have a bit of freedom there still to see
Yeah,
like which like how the benchmarks actually fall out in
yeah,
practice.
yeah. Because also once we've done the foundational structure,
With the
that
inner,
solves
yeah,
all of the levels. So the other two are optional. Then we go do the next one,
that's right. Yeah. They're just
and then
accelerators.
we do accelerators. But I think it's worth doing this because the key is like to optimize the read path, the search path, so it's super fast.
Absolutely. Yeah.
Like
I think having linear allocations here will make the Eytzinger a lot faster.
yeah,
Um,
yeah,
Contiguous arrays, I mean, yeah.
yeah.
And we can also do, yeah.
And I think we're
I'm
both
definitely happy with
excited.
this.
Cool. We excited about it. Like it's like you're thinking like, wow, this is
Yeah,
cool. Yeah,
it's definitely cool. Yeah.
yeah,
Um, I wonder if I'm always just like not wondering if RocksDB is already doing this stuff or not. Um,
Yeah, we should check. I don't think they do it across levels. But they do a whole lot of complexity though, like because of tuning. They've got
yeah,
tons of tuning knobs,
uh,
and it's like to me
exactly. But I don't know if they actually do like this kind of thing. Like I feel like we're taking our complexity in a different direction.
yeah.
Um,
Yeah,
working,
I
yeah,
I would say we don't have complexity, we have clean abstractions, like we only have one way to do something. Okay, this is now like three ways, but it's at different parts of the stack. So it's still
right.
okay. But we only have one like table layout. RocksDB will have 10 different table
Okay,
layouts.
for
Um,
different use cases. They also
yeah,
got the ribbon filters, which like turned everything on and whatnot. And yeah,
yeah,
I think they've definitely got a different philosophy than we do here, where they just like try and support every possible use case. It seems,
yeah.
and
They're like
we're targeted at our specific use case.
exactly. They're like a framework, and you can just create plugins, and they've got like hundreds of plugins. Um, but the overall framework, maybe like they don't have the incremental compaction, I think, that like we have, or they don't have the same focus on memory efficiency. So you couldn't create a forest of trees,
Yeah.
as if I understand correctly. Yeah,
Aside from the
when,
snapshots thing.
yeah, yeah, exactly. Yeah, that too. But I don't feel. Do you feel like we've got complexity so far in everything?
Not a whole lot. I think our complexity is pretty well like compartmentalized.
Yeah,
I think we do have tricky bits of the code, but I think it's overall not a very complex system.
yeah,
Um, I think the focus on keeping it deterministic keeps things a lot less complex, actually, because it just makes things everything easier to reason about. Um,
yeah. I think I feel the same. I think we've got some like the Eytzinger is difficult internally, but
right.
the external interface is a little bit difficult, but otherwise it's encapsulated, and then that's that.
Yeah. And we've got the code like very well tested now, and it took us like a week or a week and a half to do. I'm not sure how long, but
Yeah,
we just spent a good bit of time on it. But now we've got it done, and we can use it for these cool use cases to make
yeah,
things faster.
yeah,
I'm really glad we've got like a good use case for it here in the manifest stuff. Then
yeah,
I'll feel less bad about dropping it from the tables themselves,
yeah, yeah,
or from the blocks themselves.
yeah. But we
Just
are
making
actually
sure we don't.
gonna.
Yeah.
Hey, selective duplicate. Hey, how's it? We are asking, are we done with the unrolled linked list and B-tree stuff? Uh,
We just changed the design. We're doing other stuff now. Um, yeah, we've now realized that we don't need to do the unrolled linked list stuff for the smaller levels of the tree, because we can just use a contiguous array there and things will be faster. And we've also realized that instead of doing a B tree, which is essentially like a tree-based index to an unrolled linked list, like the bottom level of a B tree is an unrolled linked list actually, usually, if you want to have a good iteration. And instead of using the B tree to index that, we're going to use our other abstraction called the Eytzinger layout, which is a very cache optimized data structure for making searches over linear data fast. It's kind of like a replacement for binary search, where you like cache your keys in a special layout that's very nice for the CPU cache. And so we're going to kind of like roll our own thing where we have an Eytzinger layout to index into an unrolled linked list,
at the
essentially.
bottom. Yeah,
Except our unrolled linked list has also changed a bit, and now it's a little bit more hierarchical. Instead of just being a straight linked list, it's got like index nodes and data nodes, and you can, when you're scanning for an index, you can skip over a bunch of data nodes by looking only at the index nodes.
which is all
Um,
contiguous. Yeah,
but yeah, we haven't gotten very far in the implementation of any of this stuff yet, but our design's getting more solid and
yeah,
better, I think, too.
yeah. Yeah, what we were thinking too is kind of like we were going to do the Eitzinger layout and unrolled linked list and do that for every level. And now we've kind of realized we're going to do that for the big levels, and then for the top levels do something special. Um, yeah. But the trick with this unrolled linked list is not actually a linked list. So the name is deceptive.
Yeah.
So because linked lists we
It's
wouldn't
not linked.
touch because they've got such bad
Yeah.
performance.
We actually did now just have like a slice of pointers to nodes. So it's not linked list anymore. It's just like a segmented
Yeah,
array. I think is the better name for it, or something
yeah,
like that.
exactly. But because that's what an unrolled linked list actually is. Like you can just tune it. It's either going to be an array depending on how many elements per node. Like if you put all the elements in the node, it's an array. If you put 50% of the elements in a node, you've got almost array-like performance, but you've halved your insert costs, which is still attractive. So like that, the name is just bad. Like unrolled linked list should be some. It's basically like a list array hybrid, and you can just tune it nicely. Or
Chunky array. I don't know.
chunky array,
Yeah.
yeah, segmented array. Hey, is that what we're gonna call it?
Yeah. Segmented array seems
Yeah,
better to me.
yeah. So yeah, so Eytzinger allowed segmented array for the big bottom few levels. Top three, we're going to do something different, and then we'll see if we do something for level 0 special.
Yep. Cool. Should we start? I think we should like somehow get some of these numbers into our constants.
Yeah,
We changed now. Tables max is staying the same, but we're going to change how many levels we use, I think.
yeah,
We
6
now have
levels,
the growth factor to be 8.
8.
So we
We can put that in our config.
that means level 0 is 8. That means
Yep,
that 8 keys fit perfectly in a cache line if we have 8-byte keys.
makes sense. Eh? Genau. So we definitely going to want an
1+5
accelerator.
is 16-byte key, which is pretty
Yeah,
nice. Yeah,
yeah,
that sounds nice. Okay, so we got 8. So then level 2 is going to be, or level 1 is that. 0 is going to, yeah, so we need level +1. So this is going to our total number of, well, no, this is the level, this is level 7 or level 6 number. So
yeah.
across all levels, we get level 8 to the 7 plus 8 to the 6.
That's it.
That's across all levels. We get 2,300,000 or 400,000 roughly.
Okay.
This is level 0, level 1, level
Yeah,
2, level 3, level 4, level 5, level 6.
yeah. What is that called? Is that factorial or what is that type of number again? When
Hmm.
you they add
I
up and
think
it's
this
the
would be like the like sum. I write this like sigma, like sum um, from I equals 1 to 7, 8 to the I.
yeah,
Maybe there's a better name for it though. Um,
yeah. Cool. Okay, so that's our tables max then.
is it? I think is it 8 to the can you do factorial in Python? Import math or math dot factorial. Indeed, you can. Okay, so math dot factorial 7. No, we want actually want to like we want to do 7 plus 6 plus 5 plus 4 plus 3 plus 2 plus 1. Not factorial. That's something else.
No,
Um,
yeah,
it's not
exactly.
important.
Yeah,
We don't need to do math right now. We can just hard code this stuff.
yep.
Um,
This is
so
proper engineering, folks. Uh,
there, yeah. So table count max. So growth factor. Let
I'm
me
just kidding.
move this terminal
I'm
over
really
there.
kidding. Yeah, growth factor 8, level 6.
So now we can derive tables max from our growth factor plus the levels. You
Which
good
will
with
give
that?
us tables max. Yeah.
Equals tables max.
I think we should express these all like this, and then we should have like an assertion.
Okay, yeah. Sure.
Or actually
So
we can do this internally then. We can derive it from levels and growth factor. Is that what you were thinking?
sure, yeah.
Yeah.
Let's do that then, and then maybe boot that just in the LSM-tree file real quick.
Yeah.
And just have a constant up at the top.
Yeah.
Or I'm not sure where to put it. Maybe we should put it like down a little bit lower. Block storage, direction. Just before, okay, so LSM table count max. Now block. I'm going to say var count equals 0, well, or var level equals 0, well, level is less than config lsm levels. Table count equals level. What we need to have here, it's going to be math.power. Power. Now, wait, can we do this? Does this work with contime int? I'm not sure. How I. I think this actually works with contime int. I think it should. So we'll try that at least. Maybe it won't compile. We'll see. Oops, not there. Int, and it takes what order? X to the Y,
Yep.
taking
Times the growth factor.
config.growth factor to the power of level plus 1. Or we could do like level, yeah, I think we still want to start at level 0. We want to say have like level equals 0 here because we're calling it level 0 elsewhere in our vocabulary. And then we just return break table count. All right.
Yeah, it looks good. Power.
And then
power.
I want to assert table count equal to this. Just like have a little.
Some training wheels.
Yeah, just training wheels.
We can drop that a little bit later once we get it compiling.
Once we see that it compiles.
Yeah.
This just checks our math. We could actually like extract this to a function and like test it as well.
That would be a good way to do it. Yeah.
If we do that.
That's better. Yeah. Then we can already drop the assert. Just plug it in.
Kind of like stick it down here then maybe.
Yeah.
Or
yeah.
Equals. Yeah, then we can just have like a test case. Fn max equals, it's going to take, I guess, we don't really need to use comp time in for this. We can just use like a U32 or something. I don't know.
Yeah.
Doesn't need to be at comp time. We can just take in level count.
Yeah, or just levels and growth factor.
And then growth factor.
Yeah.
Return U32. And just do the exact same thing essentially. Table count. Or not break. Return table count. You don't need like concrete types since there's no longer comp time, not necessarily. Levels, level plus equal 1. It's not gonna be U32. should be fine for us here, I think. Yeah, that's plenty. Growth factor. All right, then we have a test. We'll count max. Try test expect equal or is beta testing. Expected is as U32, whatever that number was, this number.
Yeah.
And we will count max of well, we should just
Level
hard code them
6
here maybe.
and growth
Level
factor
6
8.
goes over.
I'm
And then
thinking
we can get rid of
maybe
this.
it maybe makes sense to put the growth factor first because the growth factor is more like it's a bigger thing, and then you kind of compounding that growth factor across levels.
Sure.
Yeah.
That's fine with me.
Yeah. It's the growth factor is like almost always 8 or 10, and then the question is more like how many levels after that.
All right.
Yeah. Nice. 8 and 6. Cool.
You stick this constant like up at the top, maybe?
Yeah, definitely.
Feels weird to have it down here. The
And the
function can
function
maybe
at,
stay here. I'm not sure.
yeah, I think the function should be at the bottom, like a helper, and then we put the const right at the top. Makes sense.
Cool. Let me just keep
Yeah,
the test by the function, which is good.
yeah,
This can just go with like block size and other things here. This needs to be
yeah,
pub. It doesn't need to be pub because we want to use in this other file now.
yeah,
Okay. Even before block size, it seems more important.
yeah,
Well, we should do it after this block storage stuff, before we do the LSM-tree.
yeah,
Where it should go. Cool. Now we've got that. So we got table count max across all levels. What do you even want to use this for? I've forgotten. We just kind of did this because we had to get rid of the old one.
yeah. We, yeah, we did
Now
get
gone
rid of
from
it.
here at least.
Yeah,
Yep.
nice. I'm really chuffed that we've got these relations worked out. I mean, it's such a simple thing, but this is going to be timeless, and just getting a proper relation, re it's really worth it. Yeah.
For sure, yeah.
I don't know, Isaac.
What can we do
I
about this?
propose what we do is like we have a quick break, like 5 minute break now. But then after the
Okay.
break, I think what we should do next is actually tackle level 0 because it's just a cache line. So like let's implement
Yeah,
it,
just
get the interface, we'll understand it for all the use cases, make it work. Then we
cool.
do the next ones, and we do the next. We can then decide
Okay.
which two we do next. But level 0 maybe is nice fun one to do.
Nice. That makes
What do you?
sense, yeah. So and then we'll just get the API down. Um, at least we'll now have the API in our mind. We want to then try and hit for the other ones, and then just get that
Yeah,
one done. Put it in its own file, I guess, and call it just like LSM manifest level 0.
yeah,
Then manifest. You can even make just manifest folder, then have like manifest just level 0. I don't know how far we're
yeah,
gonna go with that,
yeah.
but
That's cool.
yeah.
Yeah,
All right. Cool.
yeah,
Yeah. So see you back in 5 minutes then, I guess.
yeah. See you in 5. Cheers, everybody. coffee's ready.
Cool. Got my tea.
Yeah, cheers. Cheers,
Cheers.
Nipsey, everybody. Yeah.
All right. Shall we start a new file then? I think we should just like leave this one and then maybe probably delete it soon, but
Yeah.
leave it for reference for now.
Yeah. So, John Carmack,
Put on like a
make a
manifest
copy.
directory.
Yeah.
Hmm?
Yeah, that's cool.
And then we can level 0. Hub. Yes, there's a Microsoft Clippy in a Cocoon. This is the text editor I use. It's called Cocoon. I don't know if it's Microsoft. It's just like a paperclip helper thing. You like if I do like G or like it'll show me like the key bindings for the current mode I'm in. The modal editor. So if I have like some keys like you like chord keys to like use G, H or G, or like it's not actually H and L anymore because I have like different keyboard layout too. But it shows you like the keys you can use in the context, like a whole bunch of different actions. And it's a Clippy because it's kind of nice.
It's
You can get
awesome,
rid
man.
of him, but I kind of like him. Um,
Cool.
yeah, I can't use anything like Cocoon anymore either, Nipsey. It's the best. Um,
Uh,
anyhow,
um,
level 0.
Nipsey, Nipsey, did you try Sublime? Did you ever use Sublime?
Level 0. Oh, we call it. Do we want to call this like
Oh,
level
oh.
0, or do we just want to call it like linear
I
scan?
think we call it like what it is, like linear or contiguous, or
Yeah,
we
or
we could also call it
direct.
we could call it small, medium, and large. But
Okay.
I like it more the idea you were thinking, like contiguous or linear. Um,
Yeah. This one's is gonna be it's gonna be structive arrays, so we get the nice scanner for the keys.
yeah,
Um, and it's going to be um, yeah. So we just call it like linear scan because it is just a linear scan. We're not gonna do any binary search here. We're just gonna linear scan over the keys
yeah,
and find it. There's only 8
yeah,
keys, or maybe like 1 or 2 cache lines in most cases. Sometimes 4,
yeah,
but mostly usually 1 or 2. It'll always be cache
yeah,
line aligned, which is good. Um, yeah. So just or
yeah,
linear scan. Well, that's also like how lookup is. It's now describing like how the lookup works, not how it's stored, which is also not ideal. I feel like.
yeah,
So I think the other ones we might want to call them like segmented list or combined storage.
yeah, yeah. I was thinking we could also say like this one we could call Bob Dylan, the next one we call Paul, and the next one we call John. And then we can rename them later once we've got the names. But for now, this can just be Bob, Paul, and John.
We call them small, medium, and large. It's better for temporary names.
Okay, okay, cool.
Make them small for now.
Or we could do Miles, John, and Charlie, depending on the genre. Like then we're very cool, you know. Miles, John, and Charlie. Yeah. Charlie Parker, um,
Yeah,
Coltrane, and
Miles
Davis.
Davis. Yeah,
Uh,
yeah. So I'm not been clear, like totally which one's small, medium, and large.
yeah, that could cause debates. They
So
all,
I'm
yeah,
gonna go with the
all of
obvious one
them,
for now.
yeah, cool.
Um, well, it's just generic over the key, the table info, and compare key. Well, yeah, it's just table info, comp time, compare keys.
Jason messaged me in Slack. He says it's also coffee time his side, and it was 12 o'clock. So I'm just wondering, Jason, are you on the stream? Because if you are, you must say hello in the chat, please. Also, okay. We'll see. He said yesterday he
There
didn't
he
know if he wanted to put something in the chat, but yeah,
is. Just being shy, I guess.
yep.
Compare keys. What else do we need here?
Hey,
Jason is
he's here.
here. Look at that.
Uh,
We need the table info type. What else did we use for this one? No, that's it. This table info type is also generic. Okay, I see. And that's all we need for now, I guess. And
yeah,
then we're gonna need some constants too. We'll need the standard library. Just actually grab this stuff.
yep.
And config, I'm sure we'll need as well. We'll need also the LSM. Or, uh, hmm. We can use like LSM dot. Well, maybe we don't need that yet. Let's just go without that for now.
Yeah.
We should maybe then take in like the generic level, or we just assume it's level 0 for this one. I'm not sure. Um, kind of think we should just call this one level 0 to be honest, because we're not going to be using it for anything else in our code. And it makes it then more concrete and easy and more clear like what it's used for. We just call it level
Yeah.
0.
Yeah. We could also call it
And then we
overlap.
can just hard code the size too.
We could call it like, okay, level 0 is cool, or we could say overlapped, because that's what makes it different. Um, but level 0 is
Yeah,
cool.
but the size is also what makes it different.
Mm,
Like being overlapped is a property of level 0, but it's also about the size. So that we can do linear scans. Um, I think this is the way
yeah.
to go. Just call it level 0,
Yeah.
make it very concrete.
Cool.
Um,
I was thinking, Isaac, for these ones, especially for the bottom two, it would be good. Like they like level 0, they should all have the same interface. Um, so, but the thing, yeah. So say like the bottom two especially, we'll just have a function where we want to ask the manifest, please get me these tables that in this level that overlap this range. Um,
yeah,
and we'll even implement it for level 0, although we won't use it. But they'll just all look the same. So you can, because what could happen? I mean, it would be good if we could like mix and match these. Like we could use level 0 also for level 1. But maybe we don't want to do
yeah.
that. We just
I'm not
say
sure we
this
want
is
to do
the
that. I
only
think we
one
want a
that.
special case
Yeah,
level 0. I think for
yeah,
the other ones, we want to be able to mix and match them and decide like where
yeah.
the cutoff is there. Level 0 really is special
Special.
because of the
Yeah,
overlap and because the cache, like doing the linear search doesn't make sense for any other level.
yeah,
And so I think this is one is really, it's good. It's at best to just make it as concrete as possible here in the name and the
yeah.
implementation. Make it
Cool.
less, we don't want to like try and make it generic just for the purpose of making it generic because we're not going to be using it
No.
generically.
Okay.
Um, cool. So we're now going to have basically a simple array of keys. Well, we need to like have some info about table info here, I guess.
Yeah.
Um,
Our
we can just
config
like know what the fields are.
our config source path, we need to add 2 dots also, just another level.
You know,
Um,
more dots.
yep,
I'm not sure.
that's
I
it.
think we do need that config for the level size probably.
Yeah,
And here we have checksum address, key timestamp, key min, key max. So yeah, we're just gonna. I'm thinking we should make that many arrays just right in the struct here.
yeah.
Um, we could like use a multi-array list, but we don't need to. It's better to just do it like in arrays in this
Yeah,
memory.
I
I
think
think
so.
just no.
I think so too. Yeah.
Yeah.
We we had
So
something I was thinking last night. We use the hash map in standard lib. There's actually I don't know if you
yeah,
saw that issue, you know?
yeah. I saw your discussion on that.
Yeah. So I've also
Should
been thinking
find.
it makes sense. Like for some of these things, we should try to, because we need it to be deterministic, then we
Yeah.
it's almost good if we have our own structures and just test them like exactly
Hmm.
how we use them.
Especially since if the standard library is already stable, it'd be totally fine to use those, but it's not stable yet, and it won't be for a while.
And
Um,
it's going to keep
yeah.
changing between releases,
Hmm.
and then if we just upgrade to a release, we've actually got to audit like everything to check like that it has.
Exactly. Yeah. And it's better
So
actually if we just vendor stuff and then fuzz test it exhaustively, and then don't ever change it, essentially.
yeah, 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 cool.
This is going to be, what number is this? This is now config dot growth factor. Or well, we should just have a constant here that says level 0 size.
Yeah.
Const level, or just size equals
Or
config
table
dot
count.
levels, or yeah, sure, table count
Yeah.
times 1. I don't know, you want to do that times 1 there or not? It seems,
Um, it's actually the starting table count for level 0 could still be configurable, but we do elsewhere we assume that it's going to be equal to the growth factor. So I think the times 1 is fair. That's fine.
we can also just leave it off though. We can also just say it's the growth factor. Um,
Even better, like we could use our calculator to tell us what the table count should be, because that's how it calculates it for all the
yeah,
levels,
like this thing,
so that we're not getting it wrong here, if we
maximum
diverge.
max. The growth factor
Mm.
8 levels 1.
Yep, that'll tell us then the
That'll then
count.
give us levels is less than levels, so it'll just give us math to the power growth factor to 0 plus 1. So that'll be right, yeah. So it'll be, this needs
Yeah,
to be pub then. We should also add a test case for this case then.
yeah.
Whoops,
And I
I
think
messed
doing
things
it
up.
doing it this way is better. That way we don't have two
Yeah,
different ways of calculating tables
sounds
max,
good to me,
and
yeah.
getting out of
Therefore,
sync.
levels 1 should be now 8. You cool with that?
Yep.
All right. Just before I switch back to the other screen. And now we're going to do, we need LSM now.
Just quickly opening the door this side.
I feel like that should be moved to LSM.zig or something now. I'm gonna call it
Yeah,
LSM here.
yeah. It's pretty cool. I'm the only one in the office here today. So like the whole
Nice.
upper level, like the doors are open, but it's just me chilling. So this feels like vacation. This is like holiday. Yeah,
Not quite there yet. I want more sun for my holidays. We'll see
yeah,
how sunny it is in Illinois. It's usually a
yeah,
bit like less rainy in Illinois than here in Aachen in the winter. We're pretty
yeah.
rainy here in Aachen, but
Mm.
yeah, we'll see.
Are you gonna do
Well,
some
I put in the
hiking?
wrong thing here. It should be growth factor
Yeah,
for levels 1. Yeah, okay.
cool. Are you gonna do some hiking that side?
I don't know. I'm gonna try and go bouldering with my brother somewhere in southern Illinois.
Yeah,
Get some outdoor bouldering in.
yeah,
It's actually a good thing to do in winter because when the rock's really cold, then your hands stick to it better. Um, you get more
yeah,
friction, which makes things
yeah,
easier. But it's also just
yeah.
cold and miserable. But yeah.
Nice. Awesome.
Cool. I think this is now ready to go, and these are already like sorted by alignment, I think, because or well, it might have keys more than U64, but the compiler this is a jig stuck though. The compiler will pad this for us properly and get rid of the padding as much as it can.
Yeah.
We're good to go here, and now we can just do linear scans and key min. Cool. It's gonna be
Yeah.
so nice.
Are we going to do key min, key max? We got, I'm just wondering, level 0. This is where it gets interesting. Like for snapshots, um, we
Hmm.
we might want to keep track of deleted tables that the snapshots can see in level 0.
Hmm. Not quite following. What's the case that we don't support currently that would solve?
It isn't that it would solve it, but it's just that the kind of like we have to have it where the if because remember our manifest is multi-version also.
Right?
It's for the active version, but it's also for previous versions. So if someone creates a snapshot on the whole forest, then for a particular tree, they need to see level 0 as it was when they took the snapshot.
Right.
So maybe this is like a
And
big
so
spanner. Um,
so we just stored a second timestamp that says deleted timestamp.
yeah, so we'll have
Um,
created and deleted.
we can just say like snapshots may still. All right. Okay,
Yeah,
let me split these up a little bit now.
cool.
Um, all right. Do we need to like do that for all the levels? Because this is just another thing that needs to go in table info we that we're missing from this version of the struct.
Yeah,
Um,
yeah, that needs to go in table info.
we just add that here. Um,
It doesn't. You see, it depends where. Like, yeah, timestamp created, timestamp deleted. For the in memory, we will have created and deleted. For on disk, we're going to put it in different. We must still see how we do it in the on disk manifest.
well, we'll just need to. I think we should just finish the in-memory format first, and then come back to the on-disk
Exactly.
layout and see what makes the
Exactly.
most sense.
Yeah. I
And
think
what's the most
on
efficient.
disk we keep created in one side, deleted on the other, and we append them as logs, which is fine.
I think you're right. Yeah. I
Yeah.
think that ends
But
up
we
being
don't.
more efficient because then we're storing this data like out of band essentially. But
Yeah.
in memory, we want to have the same path to query both of these and not have like two different indexes for the in-memory stuff to make querying faster because that's too much overhead.
Exactly.
And so we store that in
Exactly.
band here in memory.
Yeah.
Makes sense. Cool. And so we probably
So
need that for the other levels in memory as well, though, which is much why I was adding it to this struct.
yeah. Yeah.
Cool.
Cool.
So
Then
we have like the
for
API here. I think we had like some. I think it was like this kind of API, right?
yeah,
Something like this. Without the
our
level
table
part though,
count.
the level's gone.
Yeah. Our table count is going to increase now because it's now going to go up to snapshots max.
Oh,
It's a multiplier.
we just like
Because
multiply our memory by 2 if we have 32 snapshots for like the
yeah,
whole tree.
that's why it's quite a spanner for this one. Um, the the thing is, we thought about it for the big one because there we could put it into the precedence if the key is the same. Do the and basically what we were going to do is as you're doing the search, we have an iterator, And the active tables, if you're doing an active search, there's no snapshot, then you're just querying the latest manifest. So your timestamp will always be okay. And you'll just ignore the deleted stuff.
Yep.
That's
I
the
see we
only
passed it with
challenge.
the you set pass up snapshot timestamp as max int of u64 essentially.
Yeah,
Um,
exactly. So
so
it's not a
actually that might be.
problem.
Are we using it as a tombstone though? If you guys that max int is probably wrong. I think that's our tombstone for deleted entries.
Yeah, it is. Yeah. But we could then just go one below that
Exactly, just -1.
to and reserve that also
Yeah, we'll
in
just
our
have a
timestamp.
different constant for that. That
Yeah.
works out though. Just realize we have a bug here, so should
Okay.
put that in.
Cool.
Don't forget.
Yeah.
Um, but yeah, we now need a lot more memory for level 0, so maybe it doesn't make sense to special cases anymore. And we just want to like.
Yeah.
Maybe we
Let's
should be doing
see.
this the other way around and go start the lowest levels first, and then come back up because that actually the lowest levels solve this case as well. They
Yeah.
just aren't as fast for this case as they maybe could be.
Yeah.
We go down to the bottom.
But before we do, can we just quickly check
Okay,
what it works out to? So table count is
sure.
8 times 32, so 256 tables times 16 bytes or we're looking at like 64 tables. So it's like 16 kilobytes times 30. So it's 400 kilobytes across the whole forest. So it's not a problem.
Level 0. But the problem is mainly that like the linear scan doesn't make sense anymore. Then if you have to scan past, um,
Yeah.
it's now no longer one cache line, but like yeah, 32 cache lines or 33 cache
So
lines.
I was wondering about that. I thought what we could do is make it that we sort it so that deleted tables get to the end. So they're out of. We just have that same precedence function, but we're keeping it so that it's cache line friendly, that the active manifest is going
And
to have all
so
its tables right up front.
what? Do we know where to start based on the timestamp then? Like, do you have some index of timestamp to location in the array to start the scan? Or how do we skip the deleted tables then?
We'll put the deleted. Yeah. So we will need to. The trick is that the active manifest. If let's just say like you've got like a normal read and a normal range, and then you've
Okay.
got a snapshot read and a snapshot range. So all we need to do is make sure that the normal read and normal range are optimal, and the snapshot read and snapshot range, they can be slower because they're against a snapshot. They're less common, or maybe
Are they
not,
really
but
though?
so
I
I
feel like
think
we
it
shouldn't
doesn't
special
matter.
case that. I think it's, I
Yeah.
don't know.
Okay.
I feel
So
like
I
we might
just
want to
thought that,
scrap the level 0 special case thing and kind of just move on to
yeah,
use the same code for everything. I also think building up from the bottom is the way to go here actually, because then we
yeah,
solve the general case for then work on special cases after we've got the general case solved or well.
yeah, yeah,
Um,
yeah. I
yeah, I
liked
think
I
you're right.
liked
There
your
could be.
I liked your idea for level zero a lot because what's really cool is it takes all the complexity about overlapping stuff and we deal with
Yeah,
it in one place, and it means that the others don't have to deal with it. That's why I really like it.
we can
Uh,
we can still do that.
yeah,
We just need a different approach for it, I think.
yeah.
Um, Maybe we should think of a good approach then for that, so we don't have to deal with it when we do the lower level table implementation. So then, otherwise, we're gonna have to like take that into account when we do the general implementation. We
Anyway,
might actually end up using for level 0 too. Yeah, we should solve this now if we can.
that's what I thought because this is like a very simple domain. Like it's the simplest we could possibly be.
Yeah,
So figuring out the multi-versioning here will be easier than doing it for the bigger stuff. Um,
Well, I think it's different from the lower ones because then you just kind of, I think you just stick the snapshots in the same memory. We're still bound with the same amount of disk space. I think our tables max should include snapshot tables, really, but not for the lower levels somehow. That doesn't make
Yeah,
much sense, but
I didn't
I don't
understand.
know.
I thought basically the way
That,
the way we'll solve it lower down is just our Uber precedence. So if the key is the same, then we will sort it by timestamp created. And then
yeah,
as we iterating for a snapshot read,
yeah, we just skip over the ones
we
we can't see. Yeah,
we
I'm
can't
with
see
you
and we
there.
just keep
Yeah,
going. Yeah.
but I was thinking more about the static allocation. If we were multiplying like the maximum number of tables by 30, that doesn't really work out very well anymore. Um,
It's not so bad, like it's 500 kilobytes across the whole forest.
yeah, it's not. Maybe that's fine then. We just allocate even more memory for the pool. Um, and then the cutoff or where we switch from like a contiguous array to the pool might be changed though based on how we do snapshots there.
Yeah, yeah.
Maybe we here now just do the contiguous array approach in level 0. Um, like stick all the keys, including the snapshots, in an array. Instead of doing linear scan, we just do a binary search here too.
Yeah.
And then do the same thing with scanning and skipping the snapshots that you just described.
Yeah.
Um,
Okay, cool. So are you saying we want to drop this level 0 and actually let's do our capstone, like our just have two ways of cutting up the pyramid?
yeah. Well, we may still want to keep level 0 for the special case of overlapping tables, though.
Yeah.
Implement like, but to implement that with a linear scan and or a binary search instead of a linear scan.
Okay.
Um,
Okay.
does that make sense? Maybe like
Yeah.
also allocate memory for this. I'm not sure. We want to like allocate memory or just use these arrays like they are now.
Yeah, maybe this is a problem like for stack overflow, like higher up if we've got all of this
Well, we
stuff.
can also like allocate the whole level 0 in the heap.
Yeah.
That might be simpler. If we're just storing a bunch of contiguous arrays here, we can just put this whole struct in the heap.
Okay.
To be fun. Let's just do that, I think.
Okay.
Um, and so here
Okay.
we're just gonna make table count or times. We're gonna just add times snapshots max, right?
Yeah.
I don't like that we have a snapshots max, to be honest. I think we should just like have support as many snapshots as we can with the given memory we have, with the given disk allocation we have.
Yeah.
Um,
The thing is that the more snapshots you have, the more the space amplification you have, so tables don't get released. The
right.
other thing with them is we need to record them some way. We need a list of the snapshots that have been acquired. So, like, and we record that in the super block. So we could make that part
Right.
of the trailer. We could make it variable length up to a very high snapshot max.
Yeah. But I'm not. I don't know. It just feels like we kind of like optimize the other stuff so it can just like kind of grow to meet the demands of the system. And
Yeah,
capping snapshots seems to go against that principle.
yeah, exactly.
Um,
Yeah, yeah. Cool. We can make it unlimited then. Uh,
how do we decide how big to make this allocation then, or this level 0? Like how many do we want to support then in level 0? That's then the problem that arises from that decision.
yeah,
Um,
then we don't know. Then we have to go to pooling over here.
yeah,
And this
maybe isn't
actually
the worst.
this the snapshot max thing, that also impacts the middle tier because that the contiguous allocation is not just based on the number of tables, but it's the number of tables plus the maximum outstanding snapshots
Yeah.
times the
So
maximum.
maybe we just go back to pooling for everything and not split off not make them different.
Yeah, yeah, because
Then we can
otherwise
just have as many
we
snapshots as we want. We don't actually use the snapshot max constant anywhere. We just
exactly.
deal with however many snapshots that happen to be there. Um,
Yeah,
we have a different, yeah. I think that actually works out. It's more flexible,
yeah.
and we also then don't pay the overhead at the lower levels when there's no snapshots. Um, that's the other thing. Because otherwise, when we're
Yeah,
paying a bunch of overhead to store memory for the snapshots and these linear allocations, when there probably is going to be like 1 or 2 snapshots a lot of the time,
yeah,
not close to 30.
yeah.
Um,
The only place we use snapshots max is in the super block, and even there we
right, we
can,
do that right now. We can make that
yeah,
variable length though.
yeah. But I do think like if we set snapshots max to 64, that's fine. I don't think we want it to go higher, like because
I think you're
we
probably
see
right there, but
we
yeah,
don't want it
I'm
to
just saying
be
like,
unbounded because we need to iterate over the outstanding snapshots so that we can eventually free the reference tables, things like that. So that's why we
yeah.
don't want it to. But it is nice to not, you know, I agree with you that we just actually go back to having one tier and that's it.
Well, I'm not sure we really, yeah. I'm not sure like tables being tied by snapshots is such a big issue. Is what's going to happen is that like the tables in use when the snapshot is created will get tied up, right? But we'll still be able to free like when we then after the snapshot's been created, we can still then create new tables and free those. Um,
Yeah,
like the snapshot doesn't prevent new tables being then freed that have been created since the snapshot was taken. And so just like it locks down this block of data from a certain point of time,
yeah,
and you can run out your disk faster by doing that for sure. But
yeah,
if that's the way you want to use Tiger Beetle, maybe that's fine. I'm not sure.
yeah,
Um,
yeah,
64 sounds like a very reasonable limit though. If we have to like just if you want to just like put a limit on it just to bound it.
yeah,
I think we can
exactly.
kind of write the code as if it doesn't have a strong hard limit, or so that we don't like so that we also have the fast path for when it's only like 1 or 2 snapshots.
Yeah, exactly.
Um, kind of the same way we did for manifests in the super block. Have the variable length thing
Yeah,
there to have not
yeah,
be hurt by the upper limit.
yeah. So the design doesn't require a low limit of snapshots. The design supports unlimited snapshots, but we are going to
Yeah,
cap it just to keep our CPU overhead in bounds when we're doing GCing of snapshot stuff. Just so that we know that
yeah,
like we're not going to have latency spikes or um, yeah.
that makes
But it
sense. Yeah,
does it does mean then that uh, we can't have this level 0 manifest. We also can't have the contiguous manifest. We have to go back to just doing
yeah.
pooling.
But I think it's also not bad to have the same code path for everything. It
Yeah,
seems once we get that code path done, then we're just done. I think it won't actually be that
yeah,
much faster to do these separate things because I think we're gonna make that code path pretty fast.
yeah,
Um,
yeah,
and also the difference it would make to have these smaller levels faster won't be that significant, I don't think,
mm,
because there aren't that many keys stored in them. And so it's kind of if you have 90% of your keys in the lowest level, most of your performance is dictated by how fast that level is, because that's where almost all the keys are. At
yeah,
least that's my intuition here.
yeah,
Um,
exactly. And the other thing too is that we're still going to have our object cache, which is outside of all of this.
right,
So
yeah. So that would
the
then cache
keys,
like the stuff at
the
the lower level primarily. Um,
or it's actually going to cache the stuff at the higher levels. So the stuff that's very hot.
oh yeah, that's what I meant, like the smaller levels. I just
Yeah,
misspoke.
yeah, yeah, yeah. No, cool. Yeah. So actually, those are already accelerated because we've got our cache in front.
Yeah,
If it's not in
cool.
the cache, it's almost always going to be in the bottom level anyway. So
Yeah, cool.
this has been a
Lots of design
fun.
innovations today. Yeah, we've just
Yeah,
been like slaloming,
yeah,
but we're getting it's becoming more and more clear. Like we're
yeah,
spending our time well here, I think.
yep. And we get to delete a whole directory, the manifest directory, right?
Oh yeah,
What
look
do you
at that.
think?
We can go back to
Yeah,
the old file.
yeah, cool.
Just ditch it now.
Yeah. No, it's very cool. Like I was thinking yesterday, we were still trying to solve the memory allocation problem. So we've already gone from there, like through a few, like you said, like through a few iterations.
Yep, for sure.
Yeah,
And we've got get tables. This is now back in LSM-tree. We want to go now
yeah,
to LSM man or level tree. Like
mm,
really a tree anymore. It's now a manifest level. So we're back to this
yeah,
struct essentially. We just need to
yeah,
actually implement it now and do it well.
mm,
Um,
cool.
yeah.
So
So we
we,
can get rid of this linked list stuff, I think.
yep,
We don't need that anymore. And the padding can also go.
awesome. We're gonna get rid of head and tail as well and have contiguous allocated slice of index nodes.
Yep.
So yeah, let's keep going. It seems like that was a good idea.
It applies to pointers, I think. Yeah. So these are going to be also be acquired from the pool allocator. And so we can't put them directly in
Okay.
the slice. Instead, we have got to store pointers to them.
I actually thought we were gonna do oh we only worked it out for just pointers to the index nodes. Yeah.
Yeah.
Yeah, we can't do
Otherwise, because these are all like the 4096 size. These are all 40 or
yeah,
4 kilobytes.
no. We
Yep.
can't possibly make all the index nodes statically allocated here for all
I
the
don't think so,
LSMs.
no.
No.
Because that would kind of defeat the purpose of having the pool. These also belong in the pool because they should be shared between trees and get distributed as needed.
Yeah.
Um,
Okay. But we're gonna allocate
one thing I thought,
the index nodes is actually gonna be an array because we'll know at comp time what's the max we need.
that's true, yeah. So if we pointer to an array, they'll need to store like in the count that's current, update
Yeah.
that, but that's fine.
And unless we want to do it per level, because per level we can have different amount of index nodes.
Um, I think we're gonna do this per level, yes. Um, maybe we should just do this dynamically at runtime per level to make things not too generic. Like
Mm.
we could know it because we want to have the same type for the structure for every level, and we don't want to have that dependent
Yeah.
on the level.
No.
Let's
No.
make that a slice thing. Keep it like that, and then we can store.
Yeah.
We'll know at compile time. We'll know per level basically what the maximum is here, and so we
Yeah.
can allocate that then and start. We'll just
Yeah.
pass in the level
Cool.
as like the init function.
Yeah.
I'll sketch that out real quick. Just if I init makes a level. That's all we've got so far. It's gonna return
Yeah.
itself.
And it might fail as well.
Oh yeah, it's gonna allocate memory, isn't it?
Yeah. And shall we put the allocator first and then the level?
Sure, yeah.
What do you think?
That's usually how we do it. We put the allocator first.
Yeah, because it's coming from outside even of the forest. It's got a bigger lifetime,
Yeah, the
longer
allocator is
lifetime.
we're gonna have like one at the top level and just pass it around everywhere. Put
Yeah,
all the static allocation, and we won't touch it again until we won't touch it again for ever in like the actual Tiger Beetle production
yeah,
release. Um,
yeah, yeah,
in the testing code, we will free stuff occasionally to simulate
yeah,
crashes, but yeah,
yeah. No use after freeze, right? Uh,
you know, use after freeze. Can't use after free if you never free.
yeah, we just don't free.
So our block set things kind of do free. Like we do have like these pool things are actually allocators. Like
Yeah,
our message pool is an allocator of kind of its
yeah,
sort. And so
yeah.
if we mess with the rev counting there, we can get a use after free, or essentially what the same thing as a use after free. Um,
But it's not. We'll only be stomping on our own data. We won't be going outside of the program's memory.
oh yeah, we'll still be in our address space for sure.
Yeah,
There won't be any sig fault
yeah,
from that. It just
no,
be a logic bug instead of like
yeah,
a undefined behavior thing.
yeah, yeah, exactly. Shall we actually do the init and allocate and everything and
Sure we can do that. I was thinking it might be more interesting to like look at the query path first though, to make sure we know
okay,
that this is the right way to go. So I've also
okay.
thought that we might want to take the elements or the so we're doing the Eytzinger based on data nodes now, I think, right?
Yeah,
And so
yeah.
that was our plan. And so
Yeah,
we're gonna have to
sorry,
we're gonna have
the
to have an
advantage
index
of
a
doing
function that takes
yeah, the advantage of doing the Eytzinger per data node is that we don't have to rebuild the Eytzinger every compaction. So it's quite a win.
right, yeah.
Yeah.
And so we're gonna need a function that takes like a data node index and gives you a data node that you can then binary search. It's also gonna give you we're gonna have to have a way to go from data node index to data node quickly. And
Yeah.
so that means when you scan through the index nodes looking for the data node, it might be useful then to have data node count stored in a separate slice here or an array or something to then be able to iterate over those to find the right index node without going to all these, without chasing every pointer in this slice.
Yeah. Yeah, that's brilliant. Yeah.
And then, so if we move this to like a slice of U32s here, we then have like
It's actually
index node.
elements total that we're going to put in.
No, it isn't. It's data nodes because we care about the data node index, not the element index. If we were indexing elements, then we would use elements total, but we're indexing
Okay.
data nodes
Yeah.
in the
Yeah.
Eytzinger. Um,
Cool. Cool. Yeah, okay, good.
and elements total, we might not need this anymore if we're not indexing. I think we don't need this anymore because we're not indexing based on um, element anymore. We're only indexing based
Yeah.
on going Eytzinger to data node index, and then we jump from there to the index node with the proper data node, and then from
Yeah.
there to the proper index inside the data node. And then in there we do a binary search. So we don't need to like scan for, we don't need to index based on the element anymore. So we can also just get rid of this, I
We
think.
we do, I think, for you're quite right. Like for point lookups, we don't need it anymore. But when we return an iterator where we want to do a point lookup to find the first table info, get that info back, then we want to be able to move to iterate by table info index
Right,
also. Yeah.
right. But we don't then need the fast path for skipping over index nodes because we're going to look at everything on our way. This is duplicated data. This is the sum of all these numbers in this array.
Yeah.
And this is for the fast path of iterating past index nodes. We don't actually need it to do iteration. It's
Okay.
duplicate data.
Okay, cool. Cool.
And
We
that
can
makes the
always
alignment
edit
then nice.
better.
Yeah, yeah.
Okay.
But I like it how this thing is now just only the data.
Yeah.
It feels cleaner when it's like you're only storing the actual data you need in this. And we've got the
Yeah.
counts out of band here to make things
Isaac,
faster.
just to check something quickly, like if we've done a lookup, we found the first table info in a range, and then we've got that
Yep,
table info. Now we want some kind of iterator on this level, this manifest level.
yep,
Then we want to iterate from that table info onwards. How are you thinking?
yep.
How would we do that?
Well, so once we've found the table info, we've got in our function in the context, we've got the index node and the data node, and then we just go to the next table info in that data node until the data node is empty. Then we go to the next data node in this index node until the index node is empty.
Okay,
We go to the next
okay,
index node
cool,
until that's empty, and then just keep on going. It's just a linear
cool.
scan.
Yeah,
Um,
now I understand. Perfect. So yeah, so basically our
oh,
iterator just changes. We don't store the table info index. We just store the index node and data node. Yeah,
yeah,
yeah, cool.
I'm sure, pretty sure this
Perfect.
is all the data we need to iterate efficiently, and indexed by
I,
data node. Um,
I'm with you. Thanks. I understand.
cool. All good.
Yeah.
Um,
I also like how it lines up so nicely, and it's just two things that we need.
oh yeah,
In the,
quite nice here. This one doesn't line up quite as nicely yet.
mm,
Um, we call this index node pointers and index node. Mm, index node elements would actually be the proper name for this, I think.
yeah,
Um,
because that way we keep the same style going through. You learn the one, then you know the
yeah,
other. Nice.
cool. It also lines up now. That's beautiful.
Yeah,
And then we also need
beautiful.
index node count, um, which is the number of index nodes we have here.
Yeah.
Or we can like also like modify the slices to determine the count. I don't know. We also
It's
like
not.
increment the slice length when we add a new thing
Yeah,
to it. But
yeah.
maybe let's not do
Then
that.
we,
Let's just keep
because
things
then we
simple
lose our
for now.
bounds checking here. We lose our
Yeah,
safety.
well, we could add it back.
Yeah,
But yeah, I think this is the way we
yeah,
want to do it.
yeah.
Um,
Cool. And then that'll default to zero starting off.
yep. At the beginning it is 0. And then we like
Yeah,
pull it up iteratively from disk
yeah.
on startup.
I was just wondering for our many pointer for table info under data node pointers, that field, do we actually know how many table infos there'll be?
That's
I
this
forgot.
number. We know the maximum. Um, yeah, we do know how many table. We can make this a pointer to array. You're right.
Yeah,
Um, this is going to be data node element count max. It's kind of a long variable name, but I guess it works.
yeah,
I think that's fine.
yeah,
It's a little bit long for that line, but I think it's not. It looks a little bit funny because now this looks like you're multiplying two arrays somehow.
yeah.
But if you know
What's
Zig,
the,
it works out.
yeah, what's the length of that line? Oh,
It's
okay. Oh, it's
93.
fine. Okay, so it's fine. Yeah.
Yep. We need to update this calculation because now we want to do this like differently for each level. Index node count max.
Yeah. That could be like a function, helper function,
Yeah,
or
like
do
we did the
we?
other one. We
Yeah,
then pass in a level and it calculates well, we can actually use the other helper function that tells us the number of tables per level. But then we've got snapshots in there too now. So
Yeah.
maybe that gets tricky.
We kind of don't need this index node count max because we're doing pooling, so we're not.
We need to know how long to allocate these, or how big to make these slices.
Of course.
We
Okay.
could switch back
So
to linked list and go back to pooling. That would be, yeah.
no, I think this is right, what we've got. And maybe we can jump into init now to, based on the level, work out the
Well,
table's max and go
that seems like a
backwards from
showstopper
there.
because if we're making snapshots like infinitely large, then we don't know how big to make this slice.
Oh, that's true, because snapshots don't respect the growth factor.
Right.
But even so, yesterday we weren't even thinking of when we were thinking of the just allocating the pointers for index nodes, we were actually just working off tables max. We weren't even like restricting this by
Okay,
level.
so really we can just make that tables max based for all levels then,
Yeah, and all trees. Exactly.
including level 0. It seems kind of ridiculous to use that for level 0, but maybe that's not really that bad. What is that then? That's like our Python back. So we have
Yeah.
tables max. I think I've still got. That looks right too. So we got tables max. We've got, actually I think maybe it's way at the beginning here. Keys per node.
Yeah.
Yep. So divided by keys per node is then like tables per, no. Keys per node.
That'll tell us how
We need
many
also then we need this number
data
too, like
nodes.
340, this data node count
340.
max.
Yeah.
It's still 340. I guess we can just assume it is. So we got
Yeah.
340 times keys per node. Um,
It's like
this is now like the table infos per index node. And we do tables max divided by
tables per
per
index
index
node.
node. 96.
Yeah. So it's 96 times 7 for one tree, right? For all seven, or 90, oh, it's actually only six now. 96 times six levels for one tree times 30.
96.
Um,
96 is a number. We need to multiply this by 8
eight
to get the number of 8
points. Yeah, the
plus
pointers.
4 plus the
Okay.
indexes. If we're
Okay.
doing this approach, we also put these inside the index nodes and not store this outbound and use a bit less memory for this static allocation
No,
if
it's
we
cool.
want. But then the query can get slower.
Yeah. Yeah. No, it's fine like this. So it's 96 times 12, where it's 8 plus 4, times six levels times 30 trees is 200 kilobytes. Yeah.
Yeah, that's not too bad. Okay, that seems really cheap. I like it.
Yeah. Okay. Me
Cool.
too.
We
Yeah.
just waste some memory there. It's fine. Um,
Yeah.
we'll have some extra memory at level 0, but things stay simple and fast.
Yeah.
Um,
I mean,
so we
we
do just use
never
the same
waste.
calculation then essentially.
Yeah, I mean, if you another way to think of it, like our compaction, we've saved so much memory and we've been super optimal on memory. Um, this is basically 200 kilobytes is four data blocks worth. Uh,
Right, yeah.
so
It's
we,
insignificant compared to that other stuff. Yeah.
yeah,
So
and
maybe
this is
400
like
400
really,
kilobytes.
like this is
Maybe
our
I've gotten this wrong
whole,
somehow. Maybe it's all right.
yeah,
It feels too good to be true. I don't know. Um,
yeah,
we have done this calculation here, I think. What do we get here? This index data node count max times element count max. Data node count max is 340. Element count max is um node size divided by, yeah, that's what we did that's what I did in Python, and then table count max divided by, yeah, that's the same thing I just did. So I think it works out then. Cool.
Mm.
We've already got this done now too. We just need to use div seal instead apparently because the to-do says so. Um, that's like right where we left off last time. Um,
Yeah.
it'd be funny to stop in exactly the same place as we did last time.
Yeah, should we take a lunch break now?
Are you ready for lunch break?
I'm ready. Like I think it's a good time.
Cool.
Then
And then like
we
come back at like shortly before 1 and then go until like about 2.
Yeah, exactly. Yeah. So we maybe we'll
Sounds good to
we'll
me.
take a brunch a lunch till the hour. Uh, yeah. Or
Cool.
just like 3 minutes before the hour, then we're back on.
Something like that. We'll get back just before the
Yeah.
hour. Sounds good to
Yeah.
me. Leaving off the same
Okay.
place we did last time. Back then, I guess.
Yeah, cool. Div Seal. Have an awesome lunch in the Netherlands, Nipsey, and everybody. Jason, Selective Duplicate, Larice, whoever's out there. Yeah,
Yeah.
good. Catch you now. Is it cool?
See you then.
Ciao.
Ready to get back on? Cool. All right, share my screen.
And we're back.
Cool. My screen big on the stream?
Yeah, perfect. It's big.
Cool.
Sometimes I put it so that it's like it's all the windows are equal. Like if we're just chatting
Yeah,
about the code before we diving in. But I think this morning I could have switched it a bit earlier. So, but it's yeah, you're perfect.
cool.
Yeah, I wish
I'm
we.
ready to go then when you are.
Nipsey says beer and bitterballen. Like that's my favorite Dutch food. So I wish
What
I
is
had some of that.
bitterballen? Like, is it balls of of bitter something?
Yeah, it's like stewed, slow cooked stewed meat, like beef or something, and
Okay.
it's spiced nicely, and then it's coated with crumbs, and you deep fry it. And if it's like a long round shape, it's like a croquette. Otherwise, it's bitterballen. It's like a round ball, and then you put it with like mustard on toast, and it's just the best. Because my mom
Sounds
is
pretty tasty.
yeah, my mom is Dutch, so we have it like
Yeah.
every now and then. So I'm always asking her to make it.
Cool.
Yeah, but I was a little bit late because I missed my edamame beans. They fell all over the floor, so I had to like clean it up.
Oh no.
Yeah, so
All
there we
right.
go.
So we're just coming back into this calculation here, I think. We just need to use divcl and that's done. Then we can use that to allocate. So that means we can actually make this static, just a pointer to an array then, because we
Yeah,
actually are going to allocate the same thing for every level of the tree, just so
yeah,
that we always have enough. And the overhead's not insignificant in the
yeah,
grand scale of our implementation here.
yeah.
So we're good to go there.
Cool. Then it
Um,
becomes like identical to what's inside index node, how we do the data node pointers. It's exactly.
yeah, cool. Yeah, we're good to go here.
Mm. So it's a pointer to an array which contains pointers to index nodes.
Of pointers, to nodes, which are actually
Mm.
arrays, which have a pointers to arrays.
Yeah,
It's pretty well nested here.
yeah,
We
yeah,
got pointer to array of pointers to essentially a, a array to a pointer to an array of table infos.
yeah,
We've got to chase some pointers to get there, but it's nice and hierarchical, and we
yeah.
can do it in a chunk-based allocation scheme, which is all nice.
Cool.
Right, from a pool allocator. Cool. Does this still work out? I think it should. Yeah, because we got we'll end up having. I think it's an even number then. We might end up with padding at the end. I'm not sure. Is 4096 divisible by I know it works for 32-bit systems, but I'm not sure about for 64-bit.
Yeah.
If you 4096 divided by 12, yeah, it doesn't work out evenly. We're gonna
Yeah.
have padding here.
No, that's
Darn.
okay. Yeah. It's like so
Maybe
lit.
we can. If we add one U32, then
Mm.
we're good on padding.
Yeah.
Yeah. So 4096 um minus 4, then we're good. So we just need one U32 of padding, or we can use it for something useful. Who knows? Um,
Yeah.
or total element count. We could bring that back. Um, we do. Oh, but then it's padding on a 30. Then if we have a 32-bit system, then we got padding.
Yeah.
Um, sucks.
Yeah. One little
We can make it.
distraction is when we
Yeah.
calculate remaining. we actually have less stuff to, we do node size minus
Oh,
pointer
yeah,
size
you're right.
plus, so we can,
Yeah, remaining is node size minus nothing now. So it's not just minus elements total, I guess.
yeah.
Um, so size of 1U32, that's still wrong because now we got padding.
Hmm.
Um, we should just add padding if it's a 64-byte system and add that 0. But this doesn't get rid of the disk though, so it's fine if there's padding. We don't
It's
care.
fine. Yeah, it doesn't matter. It's just
So
not used. So
yeah, we don't need to add an actual padding field though, because we don't write this thing to disk, which is what we missed yesterday.
yeah,
Um,
yeah. We just want to make sure that the index node will fit into our allocation size for our pool.
oh, this.
Mm.
There was a padding just to make this assert pass. Is that why we added it?
Yeah, and we can
Um,
actually just change the assert and say the size of the index node must be less than or equal to the node size.
okay, but it shouldn't be much less than the node size. It should be.
Yeah,
Um, we can also just say like this is like the hard requirement,
yeah,
and then like sanity check. We don't expect more than like 4 bytes of padding, I don't think.
yeah.
Um,
Perfect. I was thinking about
how's
two.
that?
Yeah, nice.
Cool.
We could just say in the comments sanity check since we don't expect more than 4 bytes of padding. Of padding. Cool.
Okay, now we've got our index node layout and we've got our this layout here. And this is all good. We need to do div seal here still. Okay, which div seal will we use today? Math.div seal.
And sorry, Isaac, our remaining calculation, that's correct now. Hey? How we do that up
Yeah, it
above.
is. Oh no,
Minus.
it
Okay.
isn't.
Okay.
We can just get rid of remaining and just use node size.
Yeah.
And can we get rid of pointer size and just use that here?
Yeah.
Uh, yeah, it just barely fits. Nice.
Nice.
That's 97 columns.
Great. Oh, so node size times the ratio. Hmm, so much better. That's really cool.
Oh yeah,
Mm.
all good. Yeah, it's just gotten simpler somehow.
Mm.
Um, that's good. We use div seal now. Div seal. We need to like to have like a. So we can use U size maybe. That's actually yeah. That's what we should use here because we can't have more than that than U
Yeah.
size count in these pointers because it wouldn't be addressable. So
Okay.
that is like the proper upper bound here for the type. And then we've got numerator is this and denominator is that. We need to catch unreachable because yeah. We really want like a helper that just catches unreachable and uses any type.
Yeah.
I'm not sure if this even works with comp time int. Oh, it does. Oh, nice. Cool. So we can actually use comp time int then. Now it gets even worse. Okay, I'm making this a helper. I'm just gonna stick it here for now. We can find a better place for it later, but
Yeah.
it'll exist now.
Yeah.
Div seal, tiger style. Um,
uh, I replied to Luke as well, you know. I don't know if you saw it.
I saw that.
Yeah, yeah.
um, tiger. Um, Um, we can actually make this one any type as well, and then like resolve. Yeah. Um, see it like this, and then we can
Uh,
use the type of
I think we should actually.
new.
Uh, hey, oh, okay. Nipsey is Luke. I didn't know that.
Yeah, yeah.
Yeah, yeah. Hey, Luke. Hey, awesome. That's even, yeah, fantastic.
I guess you didn't realize that. Okay, yeah.
I didn't know.
I'm
Yeah.
aware of these things.
Okay,
Yeah.
cool. Hey,
Um,
you
and
know
then
what?
your
I think
nominate.
it's just that this will be deprecated pretty soon, Isaac. We're gonna have to rename it. Like this, there's a big problem here. Any type is gonna have to be called duck type as well.
Have you seen my proposal? Yeah. Yeah, I think there's a much better name for this, but yeah.
Yeah,
For now, we'll use what the language gives us. Also, I
yeah,
may
yeah,
change
yeah.
my syntax highlighting to make this a keyword. This should be purple, or I'm not sure. I
Mm,
think purple is the right word, the right color for this, but it's not a type. That's
yeah,
wrong.
yeah.
Um, yeah.
I think duck type is a great name. Like, yeah.
I think it makes total sense.
Mm,
And then instead of any opaque, any type also makes more sense in my
yeah,
opinion.
yeah,
Any opaque feels a bit wrong if you like really think hard about like what it's trying to say. It's not like that the type isn't necessarily opaque that's pointing to. It's just like you can't see the type right now. So either like erased or any type is
yeah,
good because it could be any type. You need to know which type to cast it to.
yeah,
Um, Opaque would also work, but we now use that for something else.
yeah.
Anyhow, well, Nipsey, Andrew is probably not going to merge that pull request. Well, I talked to Andrew in IRC yesterday about this, and he said that he might do an executive decision this week and either merge that pull request as is or make it the call on what keyword we should use instead. Um, but if he doesn't make an executive decision, we're just going to wait until we really decide for sure and not rush things. So we don't have to break the code twice. Um, the worst part is like if we change our minds again and then break it again and then we just like
Yeah.
done like 3 iterations of keywords and broken
Mm,
everyone's code too often.
yeah.
Anyhow, div seal. It's just gonna return or math.div seal. We're gonna use and we can maybe just make this like t so I don't have to like make this line so long. Denominator catch reachable. All right.
Uh,
That's what we want. I'm not going to comment it. We can comment when we move it somewhere.
yeah.
Div seal. So now this actually is nice to use. Um, it works for time ends and doesn't need to catch unreachable. Now it works. Cool.
Can I just check it up top again quick? Just to take another look.
This?
Yeah, yeah. So we pop it in T type of numerator denominator. I didn't know type of works like that, that you can actually pass two different
So you
things.
can pass. It's really weird. I'm not sure if it's probably not going to stay this way forever. But right
Mm,
now you can pass in two arguments,
mm,
and it will then do pure type resolution between their types and give you like the pure type resolve type of this.
yeah.
This now has the same semantics as like the div floor built-in would have, for
Okay.
example,
Okay.
which
Cool.
also does pure type resolution like you would do for division normally. And
Okay.
so if you like pass in like a U32 and a U64, it'll then resolve and be this to be a U64, and
Okay.
then pass in a U64 to the deal, and then do conversion when you pass the argument here.
Okay.
Um,
Nice.
yeah,
Yeah. Perfect.
cool. In this case, it just uses comp time int, of course. But yeah,
Yeah. Yeah.
I think this is what we should have in STD math, I think. Or at least it should be the option. Anyhow, we can just have it in Tiger utils. Um,
Yeah. DJ's added his own div seal helper as well on the block
all
preset
right.
branch. So we've now got two helpers defined. Like, yeah.
Oh, I think I forgot his code now, though, don't I?
Yeah.
Where's his code? Benchmark?
It's the
Or is that
block.
in, oh, that's in the newer code, perhaps. I've got his benchmark code now in this branch.
Okay,
I
cool.
don't have his newer code yet, I don't think.
Okay.
Um, he merged the pull request last night.
Okay.
Um,
Yeah, the benchmark. Yeah.
Anyhow, we've now got our div seal, so this is not correct. So now our layout's all good.
Yeah.
So what's the next problem here? The init function's trivial right now, I think, because we know the size, and so it's just allocating these two arrays, and that's not hard to do. We should probably this get function is now completely out of date. So we maybe should update this, but
Yeah.
to get not a table info, but rather like a pointer. Well, maybe we should just like do the Eytzinger layout stuff and just get into that and see how that works out. We actually haven't looked at how much memory the Eytzinger layout will need for or how much memory we want to give the Eytzinger layout.
Yeah. Let's start off and say that we want the Eytzinger to index the first key of every data node.
Okay. And so we have the index node count max. We multiply that by the number of data nodes. We have a pretty big Eytzinger layout, perhaps. Let's see how big that gets. So,
I think it's about 64 kilobytes or so of keys.
so it could
Cool.
be.
Yeah,
I'm
let's
gonna
double
do the
check.
math.
Yeah.
We've got index node count max. I mean, we threw away all this math, didn't we? Well, I wish we could just like comp time. Someday, because they compile with like a feature, you can just like point to a variable and click on it and have comp time evaluate it for you. That'd be
Yeah.
so nice.
Yeah.
Um,
That would be really nice. Like
I
ZLS.
can't wait.
Yeah.
Yeah, well, I think the Zig compiler will just expose API to be able to do that kind of
Yeah.
stuff
Yeah.
eventually.
Yeah.
Um, and they'll just do semantic analysis of this part. Maybe we'll have to fix some compile errors first, but then it'll just like let us evaluate this expression, and then yeah,
Cool. That'll be quite something.
for sure. But for now, I just gotta have to type these things out again, I guess. Well, data node count max. This is gonna be 341 with our current distribution. With then it's actually got 33333, but we can ignore that padding.
Yep.
That's data node count max. Man, that was some pretty bad typing. Um, index node count max is going to be data node count max times
Times
data node element count max. Where's this? That's node
how?
size divided by table info.
Yeah. So node size is 496 divided by 64, roughly.
64.
Um,
So then we have data node count max times 64 equals table info per index node. Ti per index node equals. We've done this exact same thing before. I remember doing it this morning. I just lost the history
yeah.
accidentally.
Cool.
Yeah, so now we got table count max, which is config. Oh no, it's not. Hold up, this is wrong. We actually will get this from LSM now.
Yeah.
LSM dot table count max, I believe.
Yeah. It's derived there. Up top.
It's LSM table. I'm just gonna call this table count max. Oh, but now it shadows this function.
Yeah.
If we call this like get table or calculate table count max,
Yeah.
we
I
need
was
to
going to say
not shadow
calculate is good. Yeah.
for compute. Compute's a bit shorter.
Yep.
It's only two
Cool.
syllables.
Yeah.
Table count max. Then yep, and we're good there. Then we
In
just LSM.table count max.
and our
I
test,
think
we
we should
just
move
need
that
to
like to the LSM. Sorry.
our test just needs to update the reference to the function
Oh,
name
for
change.
sure.
Yeah.
Thanks. Still
Sometimes I wonder
aging
if
files.
you leave these little small changes in just to check if I'm awake.
No, I just don't really care about those little things because I know the compiler will catch them
Yeah,
eventually
yeah,
when I
yeah.
try to compile.
Yeah,
And it's good to
exactly.
keep them up to date. I just usually forget about them and catch them when I compile stuff.
Yeah, I was wondering if I should tell you because I thought, well, like we'll catch it with the compiler. And then I thought, yeah, but we are fixing the reference to the other one anyway. So then I thought, okay, well, then we can quickly fix it too.
Yeah.
Uh,
I mean, it definitely doesn't hurt to fix it now. I just like usually don't really
no,
try that hard to fix all of them,
no,
and
it
just
doesn't.
like accept that something will be updated when I compile.
Yeah, I think that's a good strategy.
Yeah, cool. Now we got table count max. That's all good. And that is, well, what is it now? It's this number where you do like, I'm just gonna type this out again. Oh, we have to
It's a
assert. It's in the test case. It's
yeah,
this.
yep.
Okay, so this times, or divided by that, right? No, yeah, it's div ceiling of these
Yeah.
things. So just divide and then so
Oh,
110. Is
yeah, yeah.
that right?
Table. No, I
That's
think that's
table count
wrong.
max divided by TI index node
Uh,
110.
oh, that's right. 110
Then
index
that's then
nodes.
multiplied 110 index nodes, yeah. And so then 110 times 340 would give us the number of data nodes, or times data node count max,
Yep.
which I think is 340
Yeah,
plus 1.
341. Yep.
So that
Yep.
gives us the number of data nodes, um,
Uh,
maximum per level tree.
yeah, and then times
You're gonna have a couple of
16, times 16 actually, that's the
key size.
mm,
Hmm. So that's 500 kilobytes Eytzinger layout. Yeah.
yeah, per level,
Per level, per
per tree.
per tree. So if you do that, then like
Yeah.
times 60
100
times 30, then you got yeah,
megs. Yeah.
100 megs. Yeah.
Yeah. So yeah, um, what is 30 times 4? It's 120. Because that's what we're spending on
Yeah.
like our mutable tables, 4 megs each.
Yeah. So the nice thing about B-tree compared to an Eytzinger layout is that it's easier for it to grow incrementally
Yeah.
as we need more nodes in our index.
Mm. But we have to allocate it anyway up front to start.
I mean,
But
like this Eytzinger layout memory.
yeah, I
Or
guess
yeah. Well, yeah.
the B tree pulls better across the trees.
Exactly. Yeah.
Yeah.
Or something B-tree like where we have like I don't know,
Yeah.
like multiple Eytzinger blocks.
Yeah. I've yeah.
That could be a thing where you've got like a tiered instead of having like a B tree tier, you have like a Eytzinger node, and then that kind of looks up which Eytzinger node child is the one you want. Um, and then that looks at the children of the children.
Yeah.
You see where I'm going with that?
Yeah.
Like we
It's
have
like a Merkle tree where you just if one of the bottom changes, you just route it all the way to the top.
something like that, yeah.
Yeah.
But when you're querying, then you have an Eytzinger layout of Eytzinger layouts essentially, and then the index shows you which child node. But then we do it all in like in this block size.
Yeah.
How many keys we fit in there? Well, I think it's only 64. Yeah, maybe that's yeah.
The
That
Eytzinger,
still works out for the
yeah, it's not bad, but it starts to really get going when you give it like a few quite a few keys. Then it
yeah.
because it's always better than binary
Also,
search. Like Eytzinger always wins over binary search as it gets bigger and bigger. It still does
the
better.
same size. Yeah. But also, there's also the thing that our Eytzinger layout is implemented on a fixed size, and so if we don't fill it up, still gonna take the same amount of time.
Yeah.
It's branchless. Um, we use Sentinels to like do partially full layouts or handle that
Yeah,
case.
that's a good point. So we don't actually want to make our Eytzinger for level 0 like
Definitely
for,
not.
yeah, yeah. That's a good point. It's so one Eytzinger is 600 kilobytes.
Yeah, that's what we calculated for.
Hmm.
Um, that'd be for all 2 million tables.
Yeah,
For yeah. Well, then place into data nodes, and all the data nodes are full too.
yeah. You see, like
You
this
know,
this problem actually gets better if you share the Eytzinger across all levels. Let's do it this way. Like let's have one Eytzinger for the whole forest. This is
yeah,
just a thought experiment. Like one Eytzinger for the whole forest is only going to cost 600 kilobytes because that's what we've worked out, right?
right, yeah,
Then we could say, okay, so that's nothing. Like 600 kilobytes, we've got one Eytzinger for the whole forest. Now it's back to like pool allocation because we're sharing, all the trees share the Eytzinger, so it's perfect.
yeah.
Then
So
what
I'm not
we
sure how we can use. Like, would that actually work in practice? Like, could we design a key that works for that? I'm not
yeah,
sure
so
we
we
could.
we don't want to do that because the keys are generic for each tree. Yeah, is that
Yeah,
am I saying that right? Have I got it the right way around? The keys are generic
yeah.
per
Like the
tree,
keys,
or the trees are
the keys,
generic
the
over
key
the
type.
key.
Exactly. Yeah.
Yeah, yeah.
Keys are generic over the key
So
type.
then what we
And
do just
yeah,
to solve that problem is we say, okay, so it's a bit awkward if we have one Eytzinger for the whole forest shared by the trees. Let's give each tree their own Eytzinger for all their levels. Then we're at 7 times 600 kilobytes, which is not bad.
okay. Well,
Uh,
6 times that.
6 times.
Well, just no.
Oh, sorry, 30. 30 times 600. Yeah. So now we're at
So,
17
well, what have
megs.
I done here? 17 megs. Yeah.
And that's not bad considering that mutable tables across all trees are 4 megabytes times 30, which is way more. So so 17 is fine because the icing, I mean, this is very important for the read the lookup path. So it's worth spending on. And then it's just a question of, okay, this is Eitzinger now for all 7 levels. Now we have to just solve the problem where for compaction, maybe what we need is like a hybrid, because you see, we were thinking, do we have the structure per tree that does the manifest for all the levels in one, or do we do it one per level? I think what we need to
Yeah.
do is have one Eitzinger for the whole tree, which is ideal for read lookups. That's much nicer than having multiple Eitzingers. Just one, and that gets you to, and then per level we then do the unrolled linked list. So we do like a hybrid structure where some of it is per level and the Eitzinger is just per tree, because that gets us away from the Eitzinger overhead.
I'm not sure that works though. Like the Eytzinger requires this linear um, list of the sorted keys that are in the layout. It gives you an index into that list. Um,
Okay, yeah, I'm with you. We could, yeah. Okay, well, one way to make it work is to put the level into the key, but that, yeah. Uh,
yeah,
then
that
we
would
have
work, but
we have to query
then
the
you
Eitzinger
can't.
multiple times.
Well, not really. It's if you well, okay, I guess that could work somehow. Then you basically then you have to query it multiple times for each level,
Yeah,
which also isn't good.
yeah.
Maybe we should go back to B trees.
I don't think so. I think the Eitzinger is first prize for the read path. It is the fastest possible thing for reads. It, it, we just have to solve this problem with allocation. This is how it comes back to pool allocation. Maybe your idea of a tree of Eytzingers is not bad. It's good. Because I mean, like, here's one option. Like, if we have an Eytzinger per tree, we can make the Eytzinger a little bit bigger. It doesn't matter if it's just a fraction bigger. If we're putting the level
Yeah,
with the key, it doesn't matter because we're still winning overall because we're winning 6 times over. Then
not yeah, it's not the size I'm worried about there though. It's more like the data layout that's then required for our people infos across the levels, because then those all have to be linear, and you then lose like you really make iteration across levels a lot slower, because then you have to skip over data from different levels as you're iterating. You're
yeah,
iterating within the level.
yeah, that's true. Because the Eytzinger is going to get you to it can get you to a specific level key, and from
Right.
then you're on your own. Then you've got to skip past data.
Mm-hmm.
So that's not great. I think there's someone out there who's saying skip list. But I
Those are
don't.
really complex.
Yeah,
I'm not sure that really solves anything for us, to be honest. It's
no,
just
we
like
don't.
adding more pointers, pointer
Yeah,
tracing.
we don't.
Uh,
Yeah, no, we don't want to do that. I think we must just figure out the Eitzinger because I think doing it is worth it for the end
yes,
result
if you do it,
for reads is great.
yes. So
Yeah,
if you do a tiered based approach, where we kind of like build a so right now our itinerary works in chunks that are powers of 2.
yeah,
Um, we could, or let's go back look at the itinerary layout real quick. Um, got like these trees here. So we've got this one tree for, let's just look at the case with 7 keys.
mm,
Whereas powers of 2 minus 1, that's right, for alignment. So we can say we could use this for 7 keys.
yeah,
And then we can also say like if you get on the high end of this, we'll go look in this other Eytzinger layout. I'm to split the Eytzinger into chunks across nodes somehow. Um, that's kind of how this idea would work. We need to have a good way to like use any arbitrary number of chunks and build a layout based on that. I think
yeah,
that can be done though. I think that just requires a bit different. It's more about how we kind of break the full range of the input into um say we've got like yeah, so I think you can only do 2 children actually. So what you do is you have and then it's not like a perfectly balanced Eitzinger layout. So maybe it hurts some cases for lookups, but it's still probably pretty fast. Um, hmm. Because either you require all the children to be like child Eitzinger layouts, or you require like just the min and or the things outside this range to be other Eitzinger layouts or something like that.
yeah,
It's not really clear to me exactly how this could work. I'm sure it could work, but I'm just not clear on the details of how it would work.
yeah,
Um, if it's still as fast as we want it to be. I think it'd still be fast if we say like just start with 1 Eitzinger. That's then enough for the first like block of keys. Then you want to add just one more block. Then what do? You like maybe you do like one comparison outside the Eitzinger layout, and then based on that jump into one of two Eitzinger layouts. Um,
yeah. I've been thinking like if we look at our index node data node, we kind of like Eitzinger is just something on top of the index. We've got data index Eitzinger, and maybe we can have Eitzinger.
yeah, that's kind of what I'm
So
proposing. I'm just trying to figure out the details of how that would work.
yeah, so we could give each level um, one block, like one 4 kilobyte of Eitzinger at the top, But yeah, then we're doing it, and if we think of Eytzinger at the tree level, the only problem is iteration. Like, how do we keep, we kind of need to be able to iterate across tables for the same level, but we need to be able to find a table in any level based on the key. Those are the two problems.
Yeah.
So given a key, find the first table in any level. Once you've found that table in a level, be able to iterate the next tables, keep those tables close together. So here's what we could do. Like if Eytzinger returns us an index. So I don't know if I'm helping, or if you want to explore something else, or I don't know
Go for it.
what are your thoughts? Otherwise, maybe I'm
I'm still thinking about things. I don't have any
okay.
concrete thoughts yet.
Hmm. Are those like the two problems we've got? Like, given the key, find a table in any level, the first table.
Yep.
Okay. And then, given a table that we found, iterate subsequent tables quickly in the same level.
That's our compaction. And then also our range queries is then iterate the same like across all levels at once for range queries.
Yeah. So I'm just wondering if we can't do something extra just to help us like solve the Eytzinger over the whole tree seems to make sense for the one problem. And I'm wondering if we can't solve the compaction iterator problem with something else, but they work together.
I'm not sure the Eytzinger tree for over the whole tree makes sense because I think it wouldn't be bad, but I think because we use like a fixed layout for Eytzinger and then use sentinels to basically pad out the max size, and we'd be paying like a constant an overhead on all our searches while the tree isn't full. I'm not sure we want to do.
Okay, because our Eytzinger is going to be
But first of all, it requires a power of 2 keys, um, or one less than the power of 2 keys.
yeah, yeah.
Um, and then it pads out to that. Um, like if you provide fewer values than you provide keys, then it'll still put the same number of keys in the layout, but use
Yeah.
sentinel keys.
So it's going to be like a megabyte of Eytzinger.
So you're gonna spend a lot more time searching this layout than you would with a
Yeah,
binary search if you had a small data set.
yeah. The other assumption that we haven't challenged so far is that we're assuming the Eytzinger is per data node. We could make it for every eighth data node, but make it over a subset. You make a mini, like a smaller Eytzinger to the actual space that we're representing.
Hmm. Or you just make it over index nodes and then do binary search inside the index node. Does that work out? Those have like a pretty fixed but small size.
Yeah,
Index node count is pretty small.
yeah,
What is it? Let's see, 110. So that we could use 128 for the Eitzinger layout. Um,
which is fine.
find the index node.
Yeah, 128
But
times 16. Um,
yeah, that's
128
a
times 16 times 6 times 30. I think it's going to be fine. Yeah, it's no problem.
360 kilobytes. Yeah,
Yeah,
that'd be fine. Does that help us significantly? I think it doesn't help us when the tree is small enough and we only have like one index node. It doesn't help us at all at the lower levels, but it's not too expensive. Um, the lower levels will only have one index node, I'm sure. Um, It's more like for the larger levels where this would help us for, but we want things to scale for the lower levels also fine. If we only have one index node, we can skip the Eytzinger layout, of course. If we
Yeah.
have like only two, we can also probably skip it, and just do like a simple comparison. I don't know. But if we have like, I don't know, at some point we want to start switch to using the Eytzinger layout to look up the index node. And inside the index node, um, yeah, then we've got to do a pretty expensive binary search here, I think. Because also, I thought of this other thing earlier, but I didn't say it yet. But if we allow data nodes to be not full, then we potentially use more memory than um, or like our maximum memory usage is unbounded actually, because we could end up in a situation where there's lots of data nodes with only one people info in them, or we're
Yeah.
not like reusing that memory.
But we can control that with we we will be compacting data nodes as part of the Unrolled implementation. Like our segmented array, we're gonna we we can
Okay.
guarantee that nodes will never be less than half full. That we can guarantee, and on average, they should be. I think you can even guarantee that they shouldn't be less than 70 or 75. But we can definitely guarantee that they won't be less than 50. We'll we'll have all that logic. Like if you are removing a table info and the tables the data node has now less than 50% full, then we will see if we can like merge it with other. I was reading it online, but that is kind of the guarantee. It's the same guarantee that the B tree gives, exactly the same. Um, yeah,
Yeah, it's the same thing.
yeah,
We need to see how that would play with index nodes then too, but I think that works out somehow.
yeah. But basically, yeah, that is true because maybe it affects then our index node count. I was thinking about it at lunch, like this is the first time we're getting into the manifest layout, and the manifest is really important. So we've only spent 2 days on it, so this is no problem. Like we must just keep going.
Yeah, I think
Um,
we should expect to find it. We should expect to spend a week on this design. I think at
yeah,
least, and
it's
then
it's a
another week on
it's
implementation.
yeah, exactly like it's totally fine if we're not coding. It's better to like get it really, really good. Uh,
Yeah, and part of me says that a B tree would actually work better than what we've come up with right now, um, and just base that off this block size we've got. And that plays really nicely with the block allocator.
yeah,
Um,
and
but
it's
I'm not
more
sure. We'd have to like.
it's simple because we don't have so
It would
much.
be. It would be a lot simpler than what we're doing right now.
Yeah,
But yeah, a B tree per level would actually work out quite well, I think.
yeah,
Um, it plays nicely with the block allocator. We can just like acquire nodes as we need them. And
yeah,
searching is O log n to find the key.
yeah,
We can even it might be fun to like put the layout of, well, I'm not sure. I'm not remembering how exactly a B tree works. We'd have to come back to this. I think there might be some fun optimizations we can do there, to, like add some like little tricks of our own.
yeah.
Um, but yeah, I think that'd be
What?
worth considering for sure. Well, I think that's like our that's like the null hypothesis here, is we just end up doing a B tree.
Yeah,
And now we need
yeah,
to see if we can beat that somehow.
yeah,
Um,
yeah. Exactly.
that's
With a
how we should
B
be thinking about this though.
with a
Yeah.
B tree, when we rebalance, like what do we do? Like do we have to actually reconstruct the whole tree sometimes if we hit a threshold or not?
No, well, if we get unlucky, we'll reconstruct. Um, we'll have to rewrite a large chunk of the tree, but we never have to rebuild it from scratch.
Mm,
Um, the the standard case is we only like touch a few nodes during rebalancing.
yeah, No, that's fine. Like it's also more general, you know. Uh,
Yeah,
I don't mind I like what we've got for index nodes, data nodes. This whole thing is very nice for iteration.
yeah. I'm worried that it's not actually very fast to query though, because the binary search you can't really. It's a lot. It's pretty expensive to jump to a specific index here. Um, that's what I'm worried about. We're kind of like doing a B tree like a tree like thing, but only with 2 levels, and really restricting ourselves because we're not getting more levels. Um,
Exactly. Yeah, yeah. That's why I thought we could just have two levels of Eytzinger. But
yeah, I'm not sure if that actually works though. I think we don't have enough memory to do that, and the Eytzinger, like the way we've designed it, doesn't really work well if it's not full. If it's full, it works really, really well. But if
yeah,
the Eytzinger layout's not filled up, then it doesn't really buy us much.
yeah, yeah.
It can actually be detrimental.
Okay.
Um, yeah,
Okay.
hard questions.
Yeah. I don't know how could we do it better? Um,
Yeah, that's what I'm trying to think of too.
if we do an Eytzinger over the whole tree and we keep the data nodes all in sort order using Uber precedence for the whole tree, that that solves the use case of reads perfectly because that's exactly what they need. And it solves the problem of static allocation because
Yep.
we're fine in our budget. So that's all fine. Then there's the other problem of iterating tables for compaction
Hmm.
and for range queries.
Well, range queries, I think actually they work perfectly there because they're already in the right order. If our precedence function is the function we would use for range queries, that would work great, right?
Okay, yeah. So range queries are solved, reads are solved.
For
Then
compaction, maybe we can just like duplicate some of the table infos and have like a separate. We have like the one like Eytzinger layout lookup, like is for just point lookups and range queries, and then we separately have for each level like a linear, the same kind of thing, but for each level separately. And
exactly,
then for
yeah.
compaction, um, we still need to do a key lookup there. Mm, I think yeah, that's because we can't like go from the Eytzinger layout to the compaction um thing.
Yeah, because Eitzinger will give us Uber precedence, not necessarily in the level we want. So we can't use
Yeah, well,
that
there'd be no way
to,
to like, get from the Eytzinger layout to get to into the compaction into the level
yeah,
at the right place if we start stuff with just one level instead of the whole tree.
yeah. If we stored if we duplicated the like the table infos per level,
Yeah, that's what I was trying to think of, but there's no way to like then get into your duplicated structure at the right place to start searching.
mm,
Then you need a different index for the duplicated structure, and then you're back to having one thing per tree. But then you also have in addition to that one thing or sorry, one thing per level.
yeah,
And in addition, you have also the one for all levels. You've just
yeah,
made used even more memory.
yeah,
Um,
yeah, exactly. Plus if the Eitzinger per tree is 17 megs, I think, then that's going to
yeah,
add some latency when we rebuild it. That latency spike will not be acceptable. Like
yeah. So what's the downside to B trees here? Like, what are we trying to improve on exactly?
They're pretty good. Like they're super competitive. Eytzinger is way faster, but B-trees are pretty awesome. Like that was the thing from array layouts. Um,
Yeah. So it's mainly the search performance that we're trying to improve on. Is that
exactly. Yeah.
right? I think
Yeah.
iteration at the lower list level of the B tree is totally fine. And memory usage seems to be better because it's easier, at least easier to fit into our stack allocation pattern. So we'll probably have less overhead of memory. So it's really just search performance we're trying to improve on then.
Yeah, but you know what, Isaac? Maybe that's a good point because I think B-tree we would have the same problem. But we're going to do B-tree per level, so then it's fine.
The B tree per level, yeah.
Yeah.
Because you don't have any problems with sharing stuff between levels then because
Yeah.
yeah, it's all incremental. Like you can
Yeah.
use as many or as few nodes as you need.
Yeah.
Um,
We understand the Eytzinger layout and we have it, and so I guess and it could be very good for lookups. Uh,
in the best case, it's excellent for lookups, but we're not really in the best case for it right now, unfortunately.
yeah.
Um,
Okay.
I'm
Any,
still thinking there's like a hybrid, like Eitzinger based B tree thing that you could use. I'm not sure about that yet.
yeah.
Um, like what is a B tree store? That's what how I get to the Wikipedia. Yeah, so at the restore keys, like on the like the so I'm telling you. So at the non-leaf nodes, you store keys and pointers to the children, right? Um, how those works? Elements and child pointers, yeah.
Yeah.
So what we can do here is we instead of making it an ordered set, we can make an Eitzinger layout of elements and child pointers.
Yeah. Yeah.
We can do an Eitzinger based B tree.
Yeah. That sounds cool.
Yeah,
Sounds
right.
it's just got to have some degree of biodigital jazz. If when it's got biodigital
I agree.
jazz, then it's Tiger Beetle. Like then we're cool. Like so, Eitzinger best features. Um,
Yeah. So in each B tree node, we make the nodes bigger, and we give an Eitzinger layout to look up the child pointer based on the
yeah,
key.
yeah.
How's that sound?
I think that sounds cool. That's awesome.
That sounds
What?
exciting to me. I think it's gonna be fast too. I think it's gonna be faster than a normal B tree. Um,
Yeah. What would a normal B tree do once you get into a node? You're doing binary search.
they do binary search, I'm
So
pretty sure,
yeah,
or a linear scan depending on how big your nodes are. Um,
and are these the internal nodes? And we are we only storing
these
the
are the
table?
internal nodes we're talking about. Yeah,
Okay, and we
and
only
then
storing the
the leaf
table
nodes are still
infos in the leaves. They still
yeah,
sorted for iteration. Yeah.
yeah.
Oh, I think that's cool then. Uh, maybe what we should do also like tomorrow is start off like take a look at what level DB do because they probably like they don't have the same static allocation requirement.
Yeah, we've looked at it already. That's not very optimal. It's pretty slow,
It's
I think, what they do.
it's just a
They've
linked
got a linked
list.
list of levels potentially, and then they've got just like some very simple like STD, C++ data structures to store the stuff.
Yeah,
Um, we should definitely look at it then just to refresh our memory though.
yeah,
Um, I should also read this Wikipedia page in full so I know what B trees are or
yeah,
know more about what B trees do.
yeah,
Um,
yeah. Because I'm not so I've never really done I've done skip lists and yeah,
I've done
like
those. Yeah, it's been a long time though. And
yeah,
it's all like there's this one CS class which is just like implement data structures in C++, and that was the whole class. And
yeah, yeah.
yeah,
I understand like a tree if you're going to disk like with the LSM tree, that's all fine. But actually that's all a B tree is as well. It's just it's the
a bit
same
different.
idea. Because I mean people even do it onto disk. Um,
Oh yeah.
you know.
Yeah, binary search is typically used within nodes to find the separation values in the geometry of interest. We should replace these binary searches within the nodes with Eytzinger layout searches,
Yeah,
and we choose our node size to be a bit larger probably. And I think this might work really well.
yeah,
Eytzinger accelerated B-tree.
yeah. Cool. You okay? So it's basically like what we've got going. Uh, it's just
Yeah,
that we're adding more levels of Eytzinger, but thinking of it properly as a
but
B
it's
tree,
more general too.
general,
It's not like fixed.
fixed height.
It's like
Yeah,
it's much more flexible.
yeah,
It's kind of like what I was trying to figure out with how I could use multiple Eytzinger layouts in different nodes, but now it makes sense because someone's already done like
yeah,
the theoretical like background to design B trees, and
yeah,
now we can just accelerate them by using a different layout instead of binary search.
yeah.
Um,
Cool.
Conceptually, we still need the same logic to choose children and to rebalance and whatnot. So that's what I
Yeah,
was getting stuck on, was like how to rebalance the Eytzinger layouts. Because I wanted like an Eytzinger layout per node essentially, and then to like rebalance them to like look up stuff in a flat array, which
yeah,
is exactly what B trees do. They just use a different layout typically.
yeah.
Um,
The only thing is if we add a child node, we will have to redo the nodes all the way up to the root. We'll have to redo the potentially redo the icing layouts all the way back up
um,
or
yeah,
not.
construction for layouts is really cheap for us though. It's linear time.
Yeah, and but I'm just wondering if we can do that. We'll we'll then have to maybe copy the keys, sort them, and then recreate the layout because otherwise we've got to jump to all the
Hmm.
other child nodes because they all formed part of that original layout.
Hmm.
Um, that's the one
We'll have to
thing
look at
is,
that. Yeah,
yeah,
it might be it might be a better way to it might be a way to incrementally update Nightsinger layout. I think there probably is. They're also a binary tree, so you can also do the same rebalancing on that. You could you could we can do like it's like the min heap thing stuff we implemented where you can like
yeah,
stick a node into a binary tree. You can do the same thing with an Eytzinger layout, I'm pretty sure. Um, I think I can figure that out with constant space with no space overhead.
yeah,
Um,
yeah. I saw from what I've seen so far is it seems to be that you can't incrementally update Eytzinger because as you it, but I
I
think
think you
that
can
is
insert stuff into it if it's not full.
exactly that's
Our
the
we're doing it a
difference.
bit
Yeah,
differently than most people do it because
yeah,
we've gone with a fixed layout, but then it can be partially full using sentinels,
yeah,
and that means that we can basically um, do the search to find the leaf node to find where the thing is in the Eitzinger layout, or maybe just do it like or have like a slower path that's not very like branchless and like weirdly um, FFS optimized, so we can
yeah,
actually understand what it's doing. But basically, just find the node, then replace that, then upheapify
yeah,
or upheap it, and
yeah,
then
yeah,
drop a sentinel from the top,
yeah.
essentially.
Cool. I'm happy. I mean, another idea is we don't have to do the Eitzinger in the B tree. We can just start with the B tree and see,
That's true. Yeah, we
because
should probably do
also
that actually,
like
or we should certainly do that. Yeah.
to close the loop, because then we can like this is all in memory. So later on, we could always come and accelerate it with Eitzinger.
Right.
What do you
So
think of that?
let's just do a B tree with a nice branchless binary search and
Yeah,
get on. Well, what else? Once we got that done, what do we need to do to close the loop? I think that's like almost it.
yeah. Then we need to do the
Filters.
forest. Yeah, but filters aren't necessary, but we need filters.
That's true.
We
But
need
it's also
the
just making stuff faster.
Yeah, we need to do the
Um,
caching layers and we need to wire up our actual storage and we need to do recovery protocol. Um,
yeah, we got some stuff to do, but now that seems all like pretty easy problems. Like I feel like we know how to do all those pretty much
yeah,
right away.
yeah.
Um, this is like
We
the
need
last really
the
open
big one.
question, I feel like.
Exactly.
Um,
And we need to do like compaction picking as well. Um,
but but that's also like based on what we do here now.
yeah,
Then we have a way to query tables, and then we can decide or just write the logic we want based on that. Yeah.
yeah. Okay. So are you happy that we just do B-tree, close the loop, and then later on we can come and accelerate it?
That sounds good to me. I think we can also maybe, yeah, I think we may come up with other ideas to optimize this over time because now we've explored the problem space pretty well like these past 2 days.
Yeah,
Um, I think B trees are really solid option from what I've seen in this
yeah,
problem space,
yeah,
especially with how they play with our pool allocator. That's a really attractive property of them.
yeah,
Um, Makes things quite simple
yeah,
to implement. And so I think just doing them right now to close the loop is I think they're actually totally adequate long term as well, even if we don't do the Eytzinger speed up. Like
yeah.
this wouldn't be our a bad corner to be backed into
No,
if we really. And so yeah,
the only other thing, right, is that if we do Eitzinger per level and we do static allocation, that was the only showstopper for that is the static allocation.
no, not really. It's also the Eytzinger layout we have um, this fixed size and it only performs at like maximum speed if it's full. If it's only 10% full, then you pay the same cost to search it as you would if it was maximum size. And because we're then doing fixed allocation for like the whole, the maximum number of tables in the whole tree, we're never actually going to reach that in practice. And so I think it's a lot
Okay.
slower. I think
Okay.
just doing binary search in that case would probably be faster.
Yeah.
Then you have the issue where you can't actually do binary search efficiently either because you don't have efficient point lookups on our skip list or our linked list thing kind of thing.
Yeah. Yeah.
I think the binary tree is the right structure here.
Yeah.
We need a tree-based structure to make lookups fast and log n. And
Yeah.
I think pretty sure we can accelerate this with Eitzinger layout too, if we
Yeah.
choose the node size as well. Not, but we don't need to worry about that yet because that's a thing you can retrofit later without changing the design. Um,
Yeah. Okay.
I think we're
Awesome.
back to
So
B trees.
back to features. Yeah.
Are
Nice.
you
What a way
happy with
to end.
enough
Uh,
digital jazz here for you?
I think it's enough digital jazz overall. Very good. Uh,
Yeah,
like half of it is also like we try to get stuff 80% good. It doesn't have to be 90%, but we're just
yeah,
having lots of little nice ideas everywhere. That's what makes it biodigital jazz at the end.
yeah.
And
I agree.
some areas like we're pretty just like routine, but that's fine.
Mhm.
Uh, but this
Cool.
is yeah, so we could take a look at level DB, but I think the B tree is already going to be like a little step ahead. Like,
Yeah, I think
uh,
so. I think they don't do B trees. They do something simpler.
yeah. Okay,
They
awesome.
also don't scale to as far as we want to scale though.
No, no. Yeah. Okay,
Around it,
cool.
they scale close. Yeah. All right. Cool.
Awesome, Isaac. You want to
Yeah.
sign us off?
Yep. Gotta get to my. Oh yeah. Um, Tiger Wheel sessions. Tuesday, 14th of December, session 3. Signing off.